So very good evening all. In the yesterday's session, we discussed about voltage commutation. Today we are going to start with the current commutation technique, right? So here it is a circuit diagram for the current commutation. In this, while discussing the operation, you will understand why it is known as the current commutation. What is the difference between the voltage commutation and the current commutation? So before moving towards the circuit operation, let us recall the two-step procedure for commutation of the SCR, right? The very first step is the current flowing through the SCR should be less than or equal to holding current value. And second step is we need to maintain a reverse voltage across the SCR for the time TC greater than or equal to TQ. TC is the circuit turn of time, TQ is the device turn of time. TQ, that is the device turn of time, this value will be specified by the manufacturer of the device, whereas the TC, circuit turn of time, this value will be specified or will be calculated by the design engineer. Okay, so here we are having the circuit diagram for the current commutation. Vs is the DC supply, right? Obviously it is the force commutation technique, so we are having the supply voltage Vs is a DC voltage. Here we are assuming the load is a highly inductive. Load is a highly inductive. So let me write here, the load is highly inductive. Load is highly inductive. If load is highly inductive, then what about the load current? Load current should be constant. Okay. So I0 is equal to capital I0. Next, so here we are having the supply Vs, here it is a load, and we are having the main switch, that is the thyristor T1. So apart from supply, load and the thyristor T1 main switch, whatever the additional elements we are having, all these are there only to commutate the SCR. Okay, to commutate the main thyristor T1. Okay, so let us understand the circuit operation. In the waveform, we are having the Ig1, that is the waveform for the gate pulse to the thyristor T1. IGA, gate pulse to auxiliary thyristor. I0, load current. IT1, thyristor T1 current. IC, capacitor current. And VC, that is the voltage across the capacitor. Okay, here we have not drawn the waveform of the voltage across thyristor T1, but we can draw if required. Okay, next, so let us start with, first of all, for t less than 0. For t less than 0, so for t less than 0, it is like circuit will be at the rest position. Okay, for t less than 0, circuit will be at the rest position, means thyristor T1, your auxiliary thyristor TA, okay, will be in the off state. T1 and TA will be in the off state. Off state. So when T1 and T are in off state, is there a path available for the charging of the capacitor? You can check here Vs, capacitor, inductor, diode D, and again back to the load. In this loop, the current can flow. Yes or no? In this loop, the current can flow, right? So to which voltage this capacitor will be charged? Yes, we'll be having the capacitor that will be charged to the voltage of this supply voltage Vs. Okay, or in other way, you can say that initially we have charged the capacitor, and that charged capacitor we have placed in the circuit. Okay, so Vc is equal to Vs. Vc is equal to Vs. To this voltage, the capacitor will be charged. This is for t less than 0. So you can check here for t less than 0, the voltage across capacitor is Vs, right? Next, now at t is equal to 0, at t is equal to 0, so voltage across capacitor is like a polarity plus here minus here, and this voltage is Vs now. This voltage is Vs now, right? Next, at t is equal to 0, we are going to apply the gate pulse to the main thyristor T1. Okay, so at t is equal to 0, thyristor T1 is turned on. So what will happen? As soon as thyristor T1 is turned on, current starts flowing from source, thyristor T1, load, and again back to the source. Means in the outer loop, the current is flowing. Okay, in the outer loop, current will flow, right? So as the load is highly inductive, so definitely the load current will be constant current. Okay, so one thing is we are having the outer loop, that is the current is flowing here in the outer loop. Next, our capacitor will try to discharge through the main thyristor, but whether this diode D will allow for the allow the reverse current through it? No. So that's why the capacitor will not discharge to the main thyristor T1. What about the auxiliary thyristor? Capacitor will try to discharge through the auxiliary thyristor, but auxiliary thyristor is in the off state, so that's why capacitor will not discharge. The meaning is after t is equal to 0 or at t is equal to 0 when thyristor T1 is turned on, okay, after that our capacitor is as the discharging path is not available for the capacitor, so capacitor will hold the same voltage that is equal to Vs. Okay, so let me draw the equivalent circuit during t is equal to 0 till t is equal to T1. Let us consider this instant is a small T1. This instant is a small T1. Okay, so during t is equal to 0 to T1, what is happening? During t is equal to 0 to T1, we have turned on the thyristor T1, right? We have turned on the thyristor T1. So here thyristor T1 is turned on, right? Next, capacitor is here. The capacitor is not discharging, okay? Because path is not available for the discharging of the capacitor, right? So we'll be having the circuit like this. Diode D will be in an off state. Auxiliary thyristor is also in an off state. And here it is a supply voltage Vs. Here we are having a load. We assume the load is a highly inductive, right? This is a Vs, capacitor C, inductor L, diode D, auxiliary thyristor TA, main thyristor T1, and here it is a load. This voltage is a V0, current I0, which is equal to capital I0. This current is a IT1. This current is a IT1, right? Now in this, if you check, the capacitor is charged to the voltage of Vs volt now with polarity plus here minus here. This voltage is Vs. Okay, capacitor is charged to the voltage of Vs volt. Okay, with polarity plus here and minus here. Now discharging path is not available, so Vc will be equal to Vs. So let me write Vc is equal to Vs. During this interval, Vc is Vs. Current is flowing from source towards the load. So can we say that IT1 is equal to I0 is equal to capital I0, right? Because only current is flowing in the outer loop only. Okay, so IT1 is equal to I0 is equal to what? Capital I0, right? What is the capacitor current? IC. Yes, IC is here. We are in the IC, so we can indicate the IC current like this. As capacitor is not discharging, so therefore IC is equal to 0 ampere only. IC is equal to 0 ampere only, right? So now you can check during t is equal to 0 to T1, Vc is Vs, IT1 I0 is equal to capital I0, and IC is equal to 0 ampere. So during t is equal to 0 to T1, if you check, first thing is IT1 I0. First thing is I0 is a constant current, that is a I0. Next, IT1 is equal to again I0. IC is 0 because capacitor is not discharging. And what about the Vc, voltage across capacitor? It is equal to Vs. Voltage across capacitor is Vs. Okay, so that will continue till T1, small T1. At small T1, we're applying the gate pulse to the auxiliary thyristor. We're applying the gate pulse to the auxiliary thyristor. So what will happen? Here it is like we're having the capacitor polarity plus here minus here. The capacitor voltage is like a Vs volt, na? So as soon as we apply the gate pulse to the auxiliary thyristor, auxiliary thyristor at t is equal to small T1, our capacitor starts discharging, na? Our capacitor starts discharging through this loop, right? So capacitor will discharge from C, TA, inductor, and again back to the C. In this loop, the capacitor discharges, and again capacitor will charge to the reverse polarity. So capacitor discharges and again charges to the reverse polarity. So you can check the waveform of Vc after T1. So after T1, here Vc waveform, it is voltage across capacitor is decreasing and again charging to the reverse polarity, right? Charges to the reverse polarity. So this voltage you can check corresponding to this, whatever the voltage we are having, this voltage is equal to minus Vs. Let me indicate here. Yeah, here we have written this voltage is a minus Vs, right? So capacitor discharges and charges to the reverse polarity. So in this loop, we are having the current that is flowing. And one current is definitely one current is flowing from source towards the load through the main thyristor, and second current is discharging current of the capacitor in this loop. Okay, So during t is equal to small t1 to small t2, can we draw the equivalent circuit during small t1 to small t2? What is happening during t is equal to small t1 to small t2? Yes, it is like a main thyristor is in a on state. Current is flowing from source towards the load. This is a load. Load current is I0 is equal to capital I0. This is a T1. This current is a IT1. This is a supply voltage Vs. This is the one loop. And second loop we are having here, it is a diode which is in a off state. Capacitor here. Here we are having an inductor and a auxiliary thyristor which is in a conduction mode. Right? So this is a TA, capacitor, inductor. Current flowing through the capacitor is a IC in this direction. We assume the IC positive means this direction, right? That is from left to right, left to right. Diode D is here, auxiliary thyristor. Capacitor voltage was at the start, it was a Vs na. So capacitor will discharge and again charges to the reverse polarity. Yes or no? Right? So if you check this loop, okay. So in this loop, the current is flowing in the anti-clockwise direction. So in this branch specifically in this branch, if you check, the direction of current which is flowing is right to left, and we have considered a IC direction is IC value will be positive if IC is having a direction from left to right. So now can you tell me, if the capacitor is discharging like this and the current in this loop is in the anti-clockwise direction, then can we say that IC will be negative here? Yes or no? Right? IC will be having, that is a negative current here. IC will be the negative current. So let me, yes, indicate this current as a I, small I. Can we write small I is equal to minus IC, or IC is equal to minus I? Yes, we can write IC is equal to minus I, right? Now, so again, let me redraw this loop. Okay, this inner loop I am going to redraw, and from that we are going to write the expression for this small I current. Okay, so you will understand that current, whatever the current will be getting, again that current will be same as that of your load commutation, because it is like capacitor initially charged to the voltage of Vs volt. We are having the passive element capacitor, and here it is an inductor as well. Okay, so let me redraw this inner loop only. So it will be like, I'm representing this inner loop only. Whatever we discussed in the yesterday session, in the same way, I'm redrawing this network or this loop. This is a passive capacitor. This voltage is Vs. It indicates the initial voltage across capacitor, na? Because left plate positive, right plate negative. Where the voltage magnitude is Vs. So I have added here Vs. That is the initial voltage, and here it is L. This current is I, and this current is I, and this current we consider it as a IC. Now can we write, yes, KVL to this loop? Yes, we can write KVL to loop. So we'll be getting, it is equal to plus Vs minus 1 by C integration of I into dt minus L into di by dt is equal to 0, right? So from this we can write, therefore Vs is equal to 1 by C integration of I dt plus L into di by dt, right? Plus L into di by dt. Next, again, we are having the same equation. Here it is a Vs, it is the integration. You can take the Laplace transform, and if we simplify it, we'll be getting it as current I. Yes or no? We'll be getting it as current I is equal to Vs into under root C by L into sine of omega 0 t. The same expression we discussed in the yesterday session. Yes or no? Right? Where omega 0 is, where omega 0 is equal to 1 by root LC. 1 by root LC. Right? So this is the expression for the current. Again, this current is sinusoidal. So this is I. So what about the IC? IC is equal to minus I, na? Right? Both are opposite. So that's why IC is equal to minus I. Therefore, IC is equal to minus I, which is equal to minus Vs into under root C by L into sine of omega 0 into T, right? This is the expression for IC current or the capacitor current, you can say, right? So if this is the expression for the IC, can we write the expression for VC? VC is equal to VC, here capacitor is discharging na, so VC is equal to 1 by C integration of IC into dt. Okay, so we can write it as, which is equal to 1 by C integration of IC, you can check it is a minus Vs into under root C by L into sine of omega 0 T into dt. So if you check, it will be equal to, we can write it as Vs upon root LC. Okay, integration of sine is minus cos of omega 0 T, that minus and this minus, it will become plus. Okay, so divided by omega 0 will be there. But what is omega 0? Omega 0 is 1 by root LC na? So can I cancel that, this root LC and this 1 by root LC? Definitely it will get cancelled out. Are you getting the point? If we put here omega 0 is equal to 1 by root LC, then that here root LC and here 1 by root LC, that will get cancelled out. Okay, so we can write it as, which is equal to Vs into cos of omega 0 into T. Vs into cos of omega 0 into T. This is the expression for the VC. This is during T1 to T2. During T1 to T2. So you can check during T1 to T2. VC, we are having it is a cosinusoidal function. IC, we are having it is a sinusoidal, but it is a negative, right? It is a negative IC we are having. So here during T1 to T2, if you check during T1 to T2, right? T1 to T2, T2 means this point. During T1 to T2, it is like a capacitor voltage is decreasing, okay, and again charges to the reverse polarity. Capacitor discharges and again charges to the reverse polarity, right? So like this. So this is a cosinusoidal. Why this is cosinusoidal? Because this capacitor current is a sinusoidal, na? Capacitor current is sinusoidal. What is capacitor current? It is a minus Vs under root C by L into sine of omega 0 T. So what is the peak value? Peak value will be Vs under root C by L, right? Definitely it will be negative, but it is a Vs under root C by L, right? So that is here minus Ip means what? Here minus Ip is nothing but, yes, this minus Vs under root C by L, right? So this is the peak value. Now you can check IC is a sinusoidal here, okay, and VC is a cosinusoidal. What about the IT1? IT1, that is the current flowing through the thyristor T1. Yes, during T1 to T2, what is IT1? You can check diode D is in off state na. So can I write IT1 is equal to I0 only, right? So IT1 is equal to I0, which is equal to capital I0, okay, right? So you can check during T1 to T2. IT1 is a constant current I0 and I0 is also constant current I0, right? This is I0, this is a constant current I0. So this is till T1 to T2. So T2 means this point, here it is T2 and here it is T2. Okay, so this will continue till T2. After T2, what will happen? Now you can check. We have turned on the auxiliary thyristor at small T1. We have turned on the auxiliary thyristor at T is equal to small T1. But at T is equal to T2, what is happening with the auxiliary thyristor? If you check at T is equal to T2, what is happening with the auxiliary thyristor? At T is equal to T2, the capacitor current reaches the zero value. Yes or no? Right? So if you check this loop, right? If you check this loop during T1 to T2, we are having the expression for this IC, okay, and the IC is reaching the zero value at T is equal to small T2. So can we say that this loop current also will be reaching the zero value at T is equal to small T2, because IC is equal to minus I, na, right? So if IC is zero, definitely or that I is also zero. Okay, so if I is zero, so what about the current flow thyristor TA? Thyristor TA current becomes thyristor TA current is equal to zero. So at T is equal to small T2, current flowing through thyristor TA becomes zero. The meaning is first condition for commutation of, yes, auxiliary thyristor has reached, right? First condition for commutation of auxiliary thyristor is, means your auxiliary thyristor will turn off at T is equal to T2. Now after that, what is expected? After that, yes, the reverse voltage should be maintained across the TA. Na? So you can check at t is equal to t2, at t is equal to t2, this current is 0, right? And you can check the voltage across the VCE1. Voltage across VCE is, it is a minus Vs, na? Voltage is negative, and it is having a value of V, it is having a magnitude of Vs. So voltage across capacitor is minus Vs. So at t is equal to t2, if we want to draw the circuit, the voltage across capacitor will be like a minus Vs, means this plate will be positive, this plate will be negative, and what is the voltage? The voltage will be Vs. Now you can check, when thyristor TA is in an off state at t is equal to t2, once current becomes to thyristor TA 0, thyristor TA turns off. After that, can we say that this capacitor voltage will appear as a reverse voltage for the auxiliary thyristor? Because for auxiliary thyristor, this is the anode and here it is a cathode, na? So this lower potential will appear at the anode, higher potential will appear at the cathode. So that's why auxiliary thyristor will feel the reverse voltage and it will turn off successfully. Are you getting the point, right? So let me draw the equivalent circuit at t is equal to t2 even. T is equal to t2. So at t is equal to t2, what is happening in the circuit? At t is equal to t2, yes, we can draw main thyristor is in a on state, right? Current is flowing from source towards the load. So here it is source. Here we're having a load. So this is a load. This is a I0, which is equal to capital I0. This is T1. This current is IT1. Okay. And what about the capacitor? At t is equal to t2, capacitor voltage is Vs only, na? But polarities are right plate positive, left plate negative. Because during t1 to t2, what happened? Capacitor has discharged and again charged to the reverse polarity. Okay. So next, here it is inductor at t is equal to t2 we are discussing, right? So, and here we are having the thyristor TA, auxiliary thyristor TA. So here it is TA. This is a capacitor. Voltage is like a, here it is a plus, here it is minus, this is a Vs, here it is a L, right? So that's why voltage across auxiliary thyristor will be like a voltage across capacitor will appear as a reverse voltage for the auxiliary thyristor. So our auxiliary thyristor will turn off. Is this clear? Now next, what will happen? After that, after T2, what will happen? Once thyristor TA turns off, because what is happening? Once capacitor charges to the polarity like plus here and minus here, then it is like our capacitor will try to discharge through this loop, but this auxiliary thyristor has already turned off, right? Next, our capacitor will try to discharge through this loop. And what about the diode? Here we are in the anode of a diode, here it is a cathode of a diode. So as soon as your auxiliary thyristor turns off, your diode D will turn on. Are you getting the point? As soon as your auxiliary thyristor turns off, diode D will turn on. Due to the forward voltage, na? Due to the forward biasing, our diode D will turn on. Diode D will turn on. So after T2, what is happening? You can check after T2. After T2, let us check for T is equal to T2 to T3. T is equal to T2 to T3. Okay. So what is happening in the circuit from T is equal to T2 to T3? So from T is equal to T2 to T3. T2 to T3. Yes, what will happen here? Once diode starts conduction, our capacitor starts releasing energy in this loop. Our capacitor starts discharging, not releasing energy. Our capacitor starts discharging in this loop. Okay. Now you can check in this loop already there is one current. Okay, that was flowing through the thyristor T1. Okay, and that current was from source towards the load. That current value was I0. Okay, means if you check thyristor T1, we are having one current already flowing from source towards the load, that is a I0. Okay, and the direction is from left to right. Second current flowing through the thyristor T1 will be your discharging current of the capacitor, and the discharging current of the capacitor direction is from right to left. So can we say that the current flowing through thyristor T1, current flowing through thyristor T1 is like a I0 minus capacitor discharging current? Yes or no? I0 minus discharging current of the capacitor. But if you recall, if you compare the previous case, that is the voltage commutation, and this case, in the previous case, yes, it was like once auxiliary thyristor turns on, yes, suddenly very high current was flowing na, so in opposition to that of the thyristor T1, because the inductor was not there in that loop. But in this case, if you check, or let me show you that loop even voltage commutation. Yes, whatever we discussed in the yesterday's session. Yes, here, as soon as your auxiliary thyristor, this is the voltage commutation. Okay, we discussed in the yesterday's session. As soon as auxiliary thyristor turns on, it is like our capacitor will try to discharge in this loop, na? And in this discharging loop, there is only, we are having only two switches, na? One is the thyristor T1, second one is the auxiliary thyristor. Yeah, we don't have any other element like a inductor or the resistor to limit the discharging current of the capacitor, right? So that's why suddenly very high current was flowing here, and immediately your thyristor T1 current, yes, it was reached to the 0 ampere at the beginning of the mode 3 only. But whereas if you check this current commutation, if you check this current commutation, here when capacitor discharges through this loop, here we are having an inductor. So whether our inductor will allow the sudden change in the current? No, right? Inductor opposes the sudden change in the current. So that's why what will happen? The discharging current of the capacitor will go on increasing slowly, right? Discharging current of the capacitor will go on increasing slowly, right? So that's why you can check after T2, you can check after T2, capacitor current increases and your thyristor T1 current decreases. We're having this type of waveform. You can check after T3, sorry, after T2. After T2, you can check capacitor current is increasing. Okay, because capacitor is discharging, na? Okay, and at the same time, thyristor T1 current is decreasing. Why the thyristor T1 current is decreasing? Because current flowing through thyristor T1 means one current is a load current minus the second current is a capacitor discharging current. So subtraction of these two currents, okay, is nothing but your IT1 now. So what is the subtraction of these two? One current is a load current, that is a I0, and second current is this current, that is a IC. So if you take the difference between this I0 minus this IC, you will be getting this type of waveform now. Well, as IC increases, this difference I0 minus IC difference decreases. So that's why here IT1 go on decreasing. At this instant, at T is equal to T3, this instant is T3, na? Here it is T3. So here, therefore, here it is T3, here it is T3, here it is T3. Let me write it as T3 here. At T is equal to T3, IC becomes equal to I0. At T is equal to T3, IC is equal to I0. So what is the IT1? IT1 is equal to I0 minus I0. So resultant current will be 0, na? Right? So that's why here you can check IT1 has reached the 0 value, right? So during T2 to T3, what is happening in the circuit? Capacitor is discharging in opposition to that of your thyristor T1. But here capacitor current, it will not increase suddenly because of the presence of that inductor. Inductor opposes the sudden change in the current, right? So that's why capacitor current will go on increasing slowly. Okay, so let me draw the equivalent circuit during T2 to T3. Equivalent circuit during T2 to T3. So during T2 to T3, if you check, definitely thyristor T1 is in an on state only. Here it is a load. This is IT1. Here we are having a capacitor C, inductor L, and diode D, which is in a on state, right? Auxiliary thyristor. Okay, this is a VS. Capacitor C, the voltage across capacitor was plus here, minus here. It was a VS at the beginning of that T2 to T3 instant. Okay, after that it decreasing. Okay, so L, diode D, and this is your IC. This is your IC, right? So you can check here, capacitor will discharge na in this loop. So here capacitor is discharging in this loop. So this current will be like your IC. And the current which is flowing through thyristor T1, one current was there. That was I0, na, load current I0. So that's why resultant current flowing through thyristor T1 is equal to I0 minus IC. Okay. So let me write IT1 is equal to I0 minus IC. I0 minus IC, right? Next, now VC go on decreasing. Okay, VC go on decreasing because capacitor is discharging, na? So VC go on decreasing. At T is equal to T3, at T is equal to T3, IC becomes equal to I0. So that's why thyristor T1 current becomes 0. Okay, at T is equal to T3, at T is equal to T3, IC is equal to I0. So therefore, what is IT1? IT1 is equal to I0 minus I0 is equal to 0 ampere. So that's why can we say that the first condition for commutation of the main thyristor T1 has reached? Yes or no? Right? So IT1 is equal to 0 ampere. The meaning is the first condition for commutation of thyristor T1 has reached. Is this clear? Means our thyristor T1 will turn off. Thyristor T1 will turn off. So at which instant our thyristor T1 has turned off? At T is equal to T3. T is equal to T3. Okay, so thyristor T1 turns off. Turns off. After that, what will happen? After that, yes, once T1 turns off, capacitor go on discharging na through C, L, D, load, and again back to the VS. In this loop, the capacitor discharges, right? In this loop, the capacitor discharges, right? But when capacitor discharges in this loop, what is the IC? Whether IC will be sinusoidal or whether IC will be constant now? When capacitor discharges in the loop C, L, D, load, and again back to the VS. So in that case, what is the IC? Whether IC will be constant current or whether it will be a sinusoidal current? Yes, it will be constant current only, right? Why? Because load is a highly inductive, na, right? So after T3, capacitor discharges and again charges to the reverse polarity. Capacitor will discharge and again charge to the reverse polarity. So you can check here after T3 the waveform. After T3, yes, if you check after T3, right? This is a T3. So here it is a T3. Here it is a T3. Okay. After T3, you can check capacitor current is constant. Capacitor is discharging. Capacitor is discharging and again charging to the reverse polarity. Means from T3 till T5. From T3 till T5. If you check, the capacitor is discharging and again charging to the reverse polarity. Right? So and through which loop? Through the load. Okay, through the load the capacitor is discharging and charges to the reverse polarity. So let me write from T3, from T is equal to T3 to T5, from T is equal to T3 to T5. Yes, we'll be having the circuit. Main thyristor in the off state. Here it is a capacitor C, inductor, diode, and here it is a load. This type of circuit we are having. This current is a constant, right? And here it is a supply voltage Vs. This is a C, L, D. Capacitor voltage was like plus here, minus here, right? This voltage is Vc now, right? Because at the beginning of T3, if you check at the beginning of this interval, actually the voltage across capacitor is VAB we mentioned. Okay, we will discuss how to find that VAB and those things. Okay, next, this current is IC. This current is IC. So capacitor discharges and again charges to the reverse polarity. So at T is equal to T5, at T is equal to T5, what is the polarity of voltage across the capacitor? It is like a plus here and minus here. And what is this voltage? This voltage is Vs. This voltage is Vs, right? So capacitor discharge and again charge to the reverse polarity. Next, during this interval, can we write IC is equal to I0, which is equal to capital I0. IC is equal to I0, which is equal to capital I0. When IC is constant, if IC is constant, what about the VC? Whether VC will be co-sinusoidal now? No. VC will be like a ramp signal now. So you can check the waveform of VC also. During T3 to T5, IC, T3 means this point till T5 means this point. Okay, from T3 to T5, IC is a constant. And what about the VC? VC is your, yes, it is a linear, right? It is a ramp signal. It is a ramp signal. Are you getting the point? It is not a co-sinusoidal. Be careful. Co-sinusoidal means this type. It is a linear now. After T3, we are having a linear. Okay, after T3, we are having a linear wave shape for the VC. For the VC. Now, at T5, what is happening? At T5, we are having circuit like capacitor has charge to the polarity like plus here, minus here, and the voltage across capacitor is Vs. So now what will happen? Our capacitor will try to discharge through this loop, but main thyristor T1 is in off state. Capacitor will try to discharge through the auxiliary thyristor. Auxiliary thyristor is in off state. Capacitor will try to discharge in opposition to that of the supply voltage, but it is like a equivalent opposite forces. So that's why resultant circuit will be at the rest position here. Okay, means at T5 our circuit operation will stop. Is this clear? Are you getting the point? Okay, so this is from T3 to T5. So now why it is a current commutation? This is known as a current commutation because if you check the IT1 waveform, you will understand. Here current flowing through thyristor T1 becomes 0. It is decreasing slowly, na? And at T is equal to T3, this current becomes 0. So first of all, current has reached the 0 value, and after that the reverse voltage is maintained. Okay. Now how the reverse voltage is maintained across thyristor T1? You can check after T3, right? From T3 to T5, what is the voltage across thyristor T1? From T3 to T5, VT1 is like this, plus here, minus here. This is a VT1. Na? So when capacitor was discharging from this loop, okay, in this loop, when capacitor was discharging, capacitor voltage was appearing as a reverse voltage now for thyristor T1. So that is nothing but your, we have maintained the, indirectly, the reverse voltage has maintained across the thyristor T1, right? So that's why thyristor T1 will turn off. Is this clear? So what is the difference between I0 and I0? Small I0 means your load current. Just we denote na IT1, I0, IC. Like that we have denoted small I0. Small I0 means load current. And that capital I0, the meaning is it indicates the load current magnitude is capital I0. Right? If load is highly inductive, why current is constant? If load is highly inductive, you can check the basic nature of the inductor. Inductor opposes the sudden change in the current, na? Right? So higher the value of the inductor, higher will be the opposition offered by the inductor to the change in current. Right? So more the inductor value, more opposition will be offered by the inductor, right, to the change in the current. So that's why as the value of the inductor is high, we'll be getting no change in the current. No change in the current means what? It is a constant current, right? Okay, next. So now this is the circuit operation. Okay. Yes. Is this clear? Current commutation, it is known as a current commutation because first of all, current flowing through thyristor T1 becomes 0, and after that the reverse voltage is maintained. But whereas in the previous case, if you check, the thyristor T1 was switched from off to the on to the off state due to the reverse voltage, na? Whatever the voltage was there across capacitor, that was appearing as the reverse voltage. So basic reason to the basic reason, okay, for the commutation of the thyristor T1 in the previous case, it was like a reverse voltage, but here it is like a current becomes 0, and due to that the thyristor is turning off. So that's why it is a current commutation, right? Now we are going to derive the expressions. If you check the GATE 2006 question paper, 6 or 7, okay, question paper, directly they have asked the numericals related to the formulas of this circuit diagram. Are you getting the point? Okay, they will give directly you the circuit diagram, and directly they have asked what is the circuit turn off time, what is the voltage across the main thyristor when it turns off. Okay, so that question you can solve only when, yes, if you recall the expressions. Okay, and those expressions we are going to derive now, right? So very important circuitry. So now yes, what is a TC here? TC means circuit turn off time. Yes, what is a TC? You can check. TC means how to find the TC. First of all, we need to check the instant at which current flowing through thyristor becomes 0. So here current flowing through thyristor T1 is reaching the 0 value at T3. At T3, at T3, what is the VT1, that is voltage across thyristor T1? You can check. Just now we discussed the once thyristor T1 turns off, the voltage across thyristor T1 is nothing but voltage across capacitor na. From T3 to T5 we discussed na. From T3 to T5, once T1 turns off, whatever the voltage across capacitor is there, that voltage will appear as across the thyristor T1. That voltage will appear across the thyristor T1. Or you can apply, yes, you can check here and you can find the VT1. So here you can check VT1 from T3 to T5 we are having VC waveform. From T3 to T5 we are having a VC waveform. So from T3 to T5, VC is like negative from T3 to T4, and T4 to T5, VC is positive. So when T3 to T4, from T3 to T4, VC is negative, means it is like a VT1 is also negative. So your thyristor T1 is in a reverse bias mode only from T3 till T4. From T4 to T5, VC is positive, means your thyristor T1 will be in a forward bias mode now. So as long as your TC is considered, we need to find the time interval. Yes, between, first of all, check the instant at which current flowing through thyristor T1 becomes 0. That is the T3. And after T3, till which time, yes, or for which interval, the reverse voltage is maintained across that thyristor T1. So you can check from T3. So here T3 means here it is T3. So from T3 till T4, only we are having the reverse voltage that will be appearing across the thyristor T1. So that's why the TC is nothing but only time corresponding to this instant, right? So that's why we have shown here as this here. Okay, this is a TC for thyristor T1, right? This is a TC for thyristor T1. So TC for thyristor T1 means it is a T4 minus T3 only. T4 minus T3. Is this clear? So we need to find the expression for that T4 minus T3 now. T4 minus T3 now. Is this clear? Right? So let me write TC for thyristor T1, or let me write here. Once thyristor T1 turns off, then VT1 is equal to VC. You can apply KVL, you will understand. VT1 is equal to VC. Okay. So therefore, TC for thyristor T1. Yes. Circuit turn off time. Circuit turn off time for thyristor T1. Right? Yes. TC is equal to, it is a T4 minus a T3. Right? So we need to write the expression for T4 minus T3 now. Okay, T4 minus T3. So how to write the expression for T4 minus T3? Let us discuss. So you can check during TC. Yes. During TC means this is during TC. What is the IC? During TC, IC is equal to I0. And what is the change in the capacitor voltage? Capacitor voltage is changing from this VAB, and here it is a 0 now. This is a VAB and here it is a 0. So can we write it as during TC, IC is equal to C into dVC by dt. But what is the IC? IC is the I0, which is equal to C into dVC, means change in the voltage across the capacitor. Capacitor voltage is here, it is a 0. Here it is like a VAB. This magnitude is VAB, but actual voltage is negative now. So that's why it is a minus VAB. Okay. So it is like a dVC is final value, that is a 0 minus this initial value. So it is a 0 minus of minus VAB. Okay. So we from that we can get the dVC. And what is the dt? Change in time is TC na? Change in time is TC. Right? So we can write during TC, yes, I am writing IC is equal to C into dVC by dt. This is standard expression for any capacitor, right? So what is the IC during TC we are having? It is a I0 is equal to C into dVC, change in the capacitor voltage. It is a 0 minus of minus VAB, right? Capacitor voltage is changing from minus VAB to the 0 now. So that's the final value minus initial value. divided by dt. Dt is a TC. So from this we can write, therefore TC is equal to C into VAB divided by I0. TC is equal to C into VAB by I0. Now the meaning is, we have got the expression for TC, but unless and until unless and until we derive the expression for this VAB, we cannot find the TC, right? Because C we know na, C they will give you in the numerical, I0 that is the load current they will give you, but the VAB we need to check, right? We need to find the VAB. So for finding the TC, we need to derive the expression for VAB now. Okay. So how to find the VAB? Again, check the waveform of VC. Check the waveform of VC, right? So VC waveform. You can check this waveform is a cosinusoidal we are having. Okay. So now whether we are having the expression for this VC waveform, whether we are having the expression for this VC waveform. Yes, we have derived na VC waveform after T1. You can check. We are having this is a cosinusoidal waveform from T1 to T2. Similarly, T2 to T3 also. T2 to T3 also you can check. IC is sinusoidal na T2 to T3, and this is also cosinusoidal. And after T3, IC is constant, so the VC is your ramp signal. Okay, means till T3, whatever the expression we are having for VC, which we have derived from T1 to T2, that expression is valid till T3. Okay, so now let me write. Yes, at omega t is equal to, yes, this is T3 na. At T is equal to T3, we are having VC is equal to minus VAB. Okay, VC is equal to minus VAB. So let me write at T is equal to T3. At T is equal to T3. Yes, VC is equal to minus VAB na. VC is equal to minus VAB. Now we're having the expression for VC. We're having the expression for VC, right? So in that expression, yes, you can check what. Yes, here we're having the expression for VC. It is a VS into cos of omega 0 t, and this expression is valid after T is equal to T1 na. This expression is valid after T is equal to T1. Okay, so you can check. Whatever the expression we have written, VC is equal to VS into cos of omega 0 into T. Okay. So for that, suppose from this instant, I have started measuring the angle. From T is equal to T1, I have started measuring the angle. Okay, or you can see the time. You can see the time. Okay. So from this time T1 till this time, okay, this total time difference is like this full time is T3, this time is T1. So what this time indicates? This time indicates your T3 minus T1. Yes or no? T3 minus T1. So now can we write here? Yes, at T is equal to T3, VC is minus VAB. The meaning is in the expression of that VC. Okay, if I put the time T is nothing but T3 minus T1. T is nothing but T3 minus T1. Then we'll be getting it as equal to, yes, VC into cos of omega 0 into T3 minus T1 is equal to minus VAB. Please try to understand this one, because this is very important, right? VC is equal to VS na, VS into cos of, right? We have written VC is equal to VS into cos of omega 0 t na. But this T means what? This T we need to check na. From T1 we need to measure the time. From T1 we need to measure the time, and till which instant? Yes, we need to measure the time till T3, because at T3 we are having it is a minus VAB. Okay, so corresponding to this, whatever the time is there means T3 minus T1. That time we need to consider, because before T1, whatever the expression we have written na for VC, which is equal to VS into cos of omega 0 t, whether that expression is valid before T1? No, that expression is not valid before T1. That expression will be valid only from T1. Is this clear? So that's why we need to measure this corresponding time. Okay, so that omega 0 into this time means what? This will be your angle na. Omega 0 into this time. Omega 0 into time means angle only. Okay, so omega 0 into this time means what? Indirectly we are writing cos of that omega 0 into this time na. So it is like cos of that angle we are writing. Okay, so corresponding this from this point till this point. Okay, whatever here we are having, right? That will be the corresponding angle we have written there. Omega 0 into this time is corresponding angle we have written. Okay. Now you can check here. Further, can we write it as T3 minus T1 as T2 minus T1 plus T3 minus T2? Please listen. T3 minus T1, can we write this time as T2 minus T1 means this time plus T3 minus T2 means this time, right? So let me write it as, therefore Vs into cos of omega 0, okay, into T3 minus T2, okay. Let me write it as omega 0 into T3 minus T2 plus T2 minus T1 plus T2 minus T1. You can check, both are having the same meaning. Okay. Right? Minus T2 plus T2 will get cancelled out. Then again, you will be getting T3 minus T1 only. Okay. Means this T3 minus T1 I have written as T3 minus T2 plus T2 minus T1. So further we can write it as, therefore Vs into cos of, yes, this can be written as omega 0 into T3 minus T2 plus omega 0 into T2 minus T1, which is equal to VAB minus VAB, sorry, minus VAB, right? Next, now you can check omega 0 T2 minus T1 means what? You can check. Here we are having omega 0 into T2 minus T1. Okay, so if you check the waveform, T2 minus T1 corresponding time means from T1 till this T2 we are having, na? T1 to T2 means this time we are having. Okay, T2 minus T1 means from this point to this point we are having. So corresponding to this, IC is a sinusoidal we are having, and it is completing one cycle, na? So if it is completing one cycle, the meaning is, what is the angle corresponding to that time? It is a pi radian. Yes or no? Right? So can we write omega 0 into T2 minus T1 is nothing but pi radian? Yes or no? Right? So let me write it as omega 0 into T2 minus T1. We need to replace, we can replace this with a pi. Okay, so it is like, therefore Vs into cos of, yes, it is a pi plus omega 0 into T3 minus T2, which is equal to minus VAB. But what is the cos of pi plus theta? Cos of pi plus theta is minus cos theta. Yes or no? Right? So we can write it, which is equal to minus Vs into cos of omega 0 into T3 minus T2 is equal to minus VAB. Is this clear? This is a cos of pi plus theta. Theta means this term now we are having. This is angle and this is a pi radian. So cos of pi plus theta, that is a cos of 180 plus theta, is a minus cos theta, na? So that's why I replaced here this I removed this pi here and I have added here minus. Okay. So now this minus will get cancel out. Okay. So therefore we can write, therefore from this we can write Vs into cos of omega 0 into T3 minus T2 is equal to VAB. This is the expression for your VAB. Expression for VAB. Once we get VAB, then only we can find TC, because TC is CVAB by I0, na? Right? So, but in order to find the VAB, we need to find T3 minus T2. Then only then it is possible to get the VAB, na? Right? So now, how to find this T3 minus T2? Let us discuss. Please check. We have already derived this expression. This is important. In order to find TC, we need to find VAB. So for VAB, we have derived the expression. But after deriving the expression for VAB, yes, now we are feeling that in order to find the VAB, we need to find the T3 minus T2. So now we are going to write the expression for T3 minus T2. Once we get that expression, from that expression, we can find VAB. And from that VAB, we can find the TC, right? So we are having total 3 important expressions, right? 2 expressions we have derived, okay? 1 more expression we need to derive, right? So T3 minus T2, we need to find. So let us check how to find T3 minus T2. So here, yes, T3 minus T2 means only this time interval, na? T3 minus T2 means from here to here. You can check, this time is T2, so here it is T2. This time is T3, so here it is T3, here it is T3, this is T3. So this indicates your T3 minus T2, T3 minus T2. Yes or no? Right? Now, can we find this T3 minus T2 expression with the help of IC? IC expression we are having. Okay, and that expression is valid after this instant. After this instant, we are having that expression valid. Now, can we write at t is equal to t3? At t is equal to t3, IC is equal to, at t is equal to t3, IC is equal to I0. Okay, at t is equal to t3, IC is equal to I0. So let me write at t is equal to t3, IC is equal to capital I0. IC is equal to capital I0. But what is the expression for IC we have derived? We know IC is negative. It is a minus Vs into under root C by L, right? Yes, here it is, minus Vs under root C by L into sine of omega 0 into t. But instead of this t, which time we need to put? We need to put the time, whatever we discussed in the VC waveform, the same time we need to put, because the t3 means this time, right? And IC expression is valid after t1. So whatever the time we're having from this point to this point, this full time we need to add, we need to put there. That is the t3 minus t1, t3 minus t1. So let me write here. Yes, IC is nothing but minus Vs into under root C by L into sine of omega 0 into, let me write it as a t3 minus t1 is equal to capital I0, is equal to capital I0. Now further what we can do, we can replace this t3 minus t1 with a t3 minus t2 and t2 minus t1, right? Like this. So it is a minus Vs into under root C by L into sine of omega 0, okay, into t3 minus t2 plus t2 minus t1 is equal to I0, right? So further this can be written as, therefore, minus Vs under root C by L into sine of omega 0 into t3 minus t2 plus omega 0 into t2 minus t1 is equal to capital I0, right? Now what is this omega 0 t2 minus t1? It is again pi, na? We discussed the omega 0 into t2 minus t1. This is t1, this is t2. Omega 0 t2 minus t1 means this time into omega 0. So that's why this angle will be pi radian. Okay, so it is a pi. So let me write it as, therefore, minus Vs into under root C by L into sine of pi plus omega 0 into t3 minus t2 is equal to capital I0, right? What is the sine of pi plus theta? Minus sine theta. Okay, so that minus, and here it is minus, that will become plus. So therefore you can write Vs into under root C by L into sine of omega 0 into t3 minus t2, which is equal to I0. So therefore from this we can write it as sine of omega 0 t3 minus t2 is equal to I0 upon, yes, Vs into under root C by L, right? What is this Vs under root C by L? It is a peak value of capacitor current, no? Yes or no? Capacitor expression we are having. Okay, so can we replace this with a peak value of capacitor current? Let me indicate it as, this is a peak capacitor current. Peak capacitor current. So let us indicate it with IC peak. Okay, IC peak, or let me write it as a IP. IP. Okay, so therefore we can write omega 0 into t3 minus t2 is equal to sine inverse of I0 divided by IP. What is IP? IP is Vs under root C by L. Okay, so this is the expression. From this expression we can find t3 minus t2. This t3 minus t2 we need to put in VAB expression, right? From this we can find VAB. This VAB we need to put in TC, right? So that we can get the TC, circuit turn of time. Is this clear? These three expressions are very important, right? Once go through whatever I have derived here, okay? Because it is only trigonometric terms, nothing else. Okay, try to understand the waveforms. Try to understand the waveforms, right? let me write where IP is equal to Vs into under root C by L. Right? So this is about current commutation technique. Okay, current commutation technique. Now let us discuss the numerical. Yes. For the current commutation circuit, C is equal to 20 microfarad, L is equal to 5 microhenry. Initial voltage across capacitor is Vs is equal to 230 volt. For a constant load current of 300 ampere, calculate first bit conduction time of auxiliary thyristor, second bit voltage across main thyristor when it is commutated, and third bit the circuit turn off time for main thyristor. Okay, second bit is important, voltage across main thyristor when it is commutated. Okay, so yes. So first of all, let us note the data. C is 20 microfarad. So it is equal to 20 into 10 to the power minus 6 farad. L is 5 microhenry. So 5 into 10 to the power minus 6 Henry. Initial voltage across capacitor. Okay, it is a 230 volt. I mean, just like whatever we considered now, before T is equal to 0, capacitor charged, okay, to the voltage of Vs volt. Same they have given. Okay, 230 volt. Means Vs is given indirectly, it is a 230 volt. For a constant load current of I0 is equal to 300 ampere. Calculate the conduction time of auxiliary thyristor. Yes, first bit conduction time of auxiliary thyristor. Yes, what is the conduction time of auxiliary thyristor? If you check the waveform, yes, from which time till which time the thyristor TA will be in the on state? It is in the on state from T1 to T2 now, right? So from T1 to T2, auxiliary thyristor is in the on state. So corresponding to T1 to T2, okay, means we need to find actually T2 minus T1. Corresponding to this T2 minus T1, what is the angle we are having? It is a pi na. So can we say that the conduction time of auxiliary thyristor is equal to pi by omega 0? Are you getting the point? Because corresponding to this T2 minus T1, T2 minus T1 means this time we are having, corresponding to this time we are having the angle pi radian, because 1/2 cycle of the sinusoidal na, right? So angle is pi radian. So therefore conduction time of auxiliary thyristor is pi by omega 0, right? Pi by omega 0. So let me write it as, yes, it is a T2 minus T1, which is equal to pi by omega 0, right? Pi by omega 0. What is omega 0? Omega 0 is 1 by root LC na? Omega 0 is equal to 1 by root LC. Yes. So which is equal to pi upon omega 0 is a 1 by root LC. So this can be written as pi into root LC. Pi into root LC. This is the conduction time of thyristor TA. So it is pi into under root L into C. What is L? 5 microhenry and 20 microfarad. Okay, so 5 into 20 into 10 to the power minus 12. So if you check, it is yes 31.42 microsecond, right? 31.42, or you can write 416 microsecond. Okay, this is the conduction time of auxiliary thyristor. Second bit, they have asked the voltage across main thyristor when it is commutated. Yes, voltage across main thyristor when it is commutated. Voltage across thyristor T1 when it commutates. Okay. Yes. Is equal to, if you check the waveform. Yes. At which instant the main thyristor commutates? At T3 na? Right? So corresponding to T3, what is the voltage across the main thyristor? That is nothing but the voltage across capacitor. So what is this voltage? This voltage is VAB na? This voltage is VAB. Here it is VAB. Okay. So here the voltage across the capacitor is nothing but the voltage across the main thyristor. Okay, which is equal to VAB. Again, this is the reverse voltage only, right? This is the reverse voltage only. So VAB. Let me write it as which is equal to VAB, right? So which can be written as VAB. We are having the expression na? We have derived VAB is equal to, yes, Vs into cos of omega 0 into T3 minus T2. Further, we need to put T3 minus T2 there, right? So first of all, let us find the T3 minus T2. It is equal to sin inverse of I0 by I peak. Okay, sin inverse of I0 by I peak. So let me write. First, let us find the T3 minus T2. That is omega 0 into T3 minus T2 is equal to, yes, sin inverse of I0 by I peak. I0 divided by I peak. What is I peak? Vs under root C by L. Okay. Where I peak is equal to Vs into under root C by L. Right. So therefore we can write omega 0 into T3 minus T2 is equal to sin inverse of, what is I0? It is a 300 divided by Vs under root C by L. Vs is 230 into under root C by L. C is given, it is a 20 microfarad, right? Yes, 20 micro. And this is a 5 micro. Next, we need to simplify it. So if you check, it is equal to sin inverse of 300 divided by 230 into under root minus 6 cancel out. So it is like 20 by 5. So it is like a 2. So if you check, this will be equal to 300 divided by 460. 40.705 degree. Okay. 40.705 degree. Right. This is your omega 0 into T3 minus T2. Now, once knowing this omega 0 T3 minus T2, now we can find VAB. So therefore, now VAB is equal to Vs into cos of this term, na? Omega 0 into T3 minus T2. So which is equal to 230 into cos of, yes, 40.705 degree. Yes, if you check, this will be equal to 174.35, right? 174.35 volt. This is the voltage VAB, but be careful, this is only magnitude. Actual voltage will be negative, right? So that's why here this is only magnitude 174.35, right? Next, the third bit they have asked for the circuit turn off time for main thyristor. TC for main thyristor, TC for T1 is equal to C into VAB divided by I0. Na? So is equal to C. It is a 20 microfarad. 20 into 10 to the power minus 6 into 174.35 divided by I0 is a 300. So if you check, it is equal to 11.62 microsecond, right? This is your TC for thyristor T1. Is this clear? Right? Okay. The same example they asked, you can refer the previous question paper, I think GATE 2006 or 2007. and as it is, this numerical is given in the PS Bimra book. Okay, and as it is, that question they asked in the GATE examination, right? Okay. Next. Yes, it is better to memorize these expressions. Okay. Yes, yes, yes. Okay. Last part. This expression we derived na TC, which is equal to CVAB by I0, right? Okay. Am I not audible? Pratik, please check once. Okay, okay, okay. Right? So next, let's discuss one more question. Yeah, this is a bit interesting. This question, if you check in our booklet, actually this is a linked answer type question. Means on the answer of this question, the next question's answer will be dependent. Okay, so it is given under the chapter DC to DC converter. As in the yesterday's session, I told you, in the DC to DC converter also we are having the voltage commutated chopper and current commutated chopper. The same commutation circuitry we are having. The only thing is we are using this circuitry as a chopper there. Okay, so this part, these questions were discussing in the chapter number 1, under chapter number 1. Okay, so these two questions will not be we are not going to discuss during the DC to DC converter. Okay, so let us read it. A LC circuit shown in the figure has an inductance L is equal to 1 millihenry and a capacitance C is equal to 10 microfarad. The initial current through the inductor is 0, that is a rest position, while the initial capacitor voltage is 100 volt. Capacitor initial voltage is given 100 volt. The switch is closed at T is equal to 0. The current IC through the circuit is, and they have given the 4 options. Yes, can anyone? We are having LC circuit, single loop we are having, simple. In that capacitor is initially charged. Then what will be the expression for the current in the circuit they have asked? This type of circuit we have already derived the expression. How I am representing this circuit as here we are having a capacitor and its initial voltage as well, na? Right? So what we need to do? We need to represent this loop or this this loop as a L, that is a passive element inductor, passive element capacitor, and a voltage source of 100 volt. Right? And like this we can simplify. We already derived the expression. You can check Vs under root C by L into sine of omega 0 t, na? Yes. Let me redraw this. At T is equal to 0, the switch is closed. Okay, so for T greater than 0. Okay, if we want to draw this network, it will be like this. Capacitor, and here it is the initial voltage, right? What is the circuit current they have asked? This is a L. L value is 1 millihenry and C value is 10 microfarad. And this voltage is initial voltage across capacitor. Yes, we are having DC supply and inductor and capacitor. Now can we write the expression IC? So IC is equal to what? It is a Vs. Instead of Vs, now we are having the 100 volt, na? So it is 100 into under root C by L. C is 10 microfarad, 10 into 10 to the power minus 6 divided by L. It is a 1 into 10 to the power minus 3. Right? It is a Vs under root C by L. Na? So Vs in our case, it is 100 volt now. And C is the capacitor. L is a 1 microhenry, 1 millihenry. Okay? Into sine of omega 0 into T. Omega 0 into T. That omega 0 we need to find. Okay? So first of all, let us check. Therefore, IC is equal to this term. Check, this term will be equal to 100 into under root that will be like 10 to the power minus 2. Okay? Into sine of omega 0 T. Yes, it is a 10 into sine of omega 0 T. So it is a IC. Now what is omega 0? Omega 0 is equal to 1 by root LC. Na? We know it is a 1 upon root L is, yes, 1 millihenry, and C is 10 microfarad. So if we check, therefore omega 0 is equal to, yes, it is like 1 upon under root minus 9 minus 8, no? 10 to the power minus 8. So it will be like 10 to the power 4. Okay, omega 0. So therefore IC is equal to 10 into sine of 10 to the power 4 into T, right? This is the expression for the capacitor current or the current in the circuit. So if you check the options, correct option is option D, right? 10 into sine of 10 to the power 4t. Is this clear? Next. Now let us discuss the second question. That question depends on whatever the expression we have derived here. Okay. So that's why it is a linked answer question. Okay. Linked answer question. So yes. So here it is a question. The LC circuit shown in the above question, that is the previous question, is used to commutate a thyristor, which is initially carrying a current of 5 ampere. Okay. As shown in the figure below. The values and initial conditions of L and C are the same as in above question. The switch is closed at t is equal to 0. If the forward drop is negligible, the time taken for the device to turn off is. Okay. So it is given that whatever the LC circuit means, this LC circuit now we discussed in the previous question. This LC circuit we have connected here. It's just like across the thyristor. This thyristor, yes, was initially carrying a current of 5 ampere and the direction of current is from left to right. Now, our task is to find the time taken for the device to turn off. We need to find the time taken for the device to turn off. It is not meaning that it is not like a circuit turn off time. Please don't get confused. Our task is to find the time taken for the device to turn off. Means if I close this switch at t is equal to 0 now, if I close this switch at t is equal to 0, from t is equal to 0 till which instant our thyristor will be in the on state. Okay, that we need to find. Time taken by the device to turn off means, yes, because you can check in this circuit, if at t is equal to 0 switch is closed, the current will be flowing into this circuit. It is like this I, and this current is like a opposite current for the thyristor. In the thyristor, we are having one current is 5 ampere. Second current is that is current in this loop. That is the current I. Okay. So resultant current in the thyristor will be 5 ampere minus this I na. And once that 5 ampere minus I reaches 0, then and only then our thyristor will turn off. Is this clear? Are you getting the point? Okay. Means we need to find the instant at which current flowing through thyristor becomes 0. Now current flowing through thyristor will reach the 0 value where this current I reach the 5 ampere na? Because you can check here current is 5 ampere constant, which is flowing from left to right. second current flowing through the thyristor is, that is the current I, that is the opposite to that of a 5 ampere. So the resultant current, if we want to be 0, okay, then it is like a current I should be equal to 5 ampere. Means once current I reaches 5 ampere, our thyristor will turn off. Is this clear? Right? So now let us check the same circuit, and for this circuit we are having the current expression we have derived in the previous example. That expression we need to use here. Okay, so let me write. For t greater than 0, for t greater than 0, it is like a switch is closed, switch is closed. Here it is inductor, here it is like a capacitor we are having. Okay, here it is a thyristor which is in a on state. Let me show it as an on state. This switch is closed at t is equal to 0. Okay, switch is closed at t is equal to 0. Inductor, capacitor, initial voltage is there definitely, plus minus 100 volt. And let us consider current in this circuit is I. This is a 5 ampere. And let us consider this current is a IT1. Current flowing through thyristor T, let us consider it as a IT. Instead of IT1, let us write it as a IT. Right? So this is a IT. Now can we write IT is equal to 5 minus I? Right? IT is equal to 5 minus I. Okay. And what is the expression for this current I? Whatever we written in the previous example, right? Same expression we need to put here. Okay. So therefore we can write IT is equal to 5 minus, what is the I we have written? 10 into sine of 10 to the power 4 into t. Na? Same expression we have written. Now if you check, our thyristor will turn off when this IT becomes 0. Okay. So for the thyristor to commutate, thyristor to commutate, yes, IT should be equal to 0 ampere. Na? Because very first condition for the commutation is SCR current should be less than or equal to the holding current value. Should be less than the holding, not equal to, should be less than the holding current. Okay. And holding current, they have not mentioned anything, right? So that's why by default, we need to consider it as a 0 ampere. Okay. So IT is equal to 0 ampere. Next. So here we can put here 0 is equal to 5 minus 10 into sine of 10 to the power 4 into t. So from this can we write, therefore 5 is equal to 10 into sine of 10 to the power 4 into t. Now from this, can we find the t? Yes, we can find. So therefore sine of 10 to the power 4 into t is equal to 0.5, right? So therefore we can write 10 to the power 4 into t. 10 to the power 4 into t is equal to sine inverse of 0.5. So if you check, it is a 30 degree, but in radian we need to write it is a pi by 6 radian. Right? We need to write this angle in a radian, not in degrees. Please be careful, because here we need to find the time t. Na? So in order to find the time t, we need to write this angle in radian only. If you put it as a 30 degree, 30 divided by 10 to the power 4, and if you check the answer, that answer will not match your whatever the options they have given. Okay. So keep it in mind. Sine inverse of this 0.5. If at the left hand side, yes, this, if we consider this as a angle, then that 30 degree, okay. But in order to find the that t, we need to consider that angle in terms of your radian equivalent. Okay. So therefore t is equal to pi by 6 divided by 10 to the power 4. So if you check, it is equal to yes 52.36 microsecond, right? 52.36 microsecond. So if you check the options, yes, 52 microsecond, correct? The meaning is, please try to understand the meaning. Okay. At t is equal to 0, we are closing this switch. And after that, this current starts increasing now, because this current is a sinusoidal. So this current starts increasing. And at t is equal to 52 microsecond, the current in the circuit will reach the 5 ampere. So that's why opposite current 5 ampere, right? And left to right current is also 5 ampere. So resultant current in the circuit will reach the 0 value. So that's how our thyristor will turn off. Okay. And the meaning is time taken for the device to turn off means what? From 0 till that 52 microsecond. Okay. Thyristor current go on decreasing, and at 52 microsecond, thyristor current becomes 0. Okay. So that's why that is the time taken for the device to turn off is nothing but that time. Okay. So it is a 52 microsecond. Is this clear? Right? Okay. What about reverse hold time? What do you mean by the reverse hold time, Akshay? Right? Okay. Okay. Yes, definitely. SCR will not allow the current from cathode to anode, but you can check the how the currents we are having. One is 5 ampere, second one is the opposite current, na? And that opposite current is less than 5 ampere till 52 microsecond. So resultant current will be in the forward direction only, na? At a 5 microsecond, at 52 microsecond, both are reaching the same values. Okay. So I becomes equal to 5. So current becomes 0. So you can check after 52 microsecond whether the current will flow through the thyristor. No. Right. So we'll discuss all the doubts after the or at the end of the session. Right. Yeah. So now next. So till now we have discussed about how to turn on the SCR, how to turn off the SCR. Okay. And SCR characteristics during turn on, during turn off, and its static VI characteristics. Now we are going to discuss the thermal modeling of SCR. Okay. Very simple bit. Sometimes they have asked the question. Okay. And very small bit we are having. Basically, it is related with the analogy between thermal energy and electrical energy. Right. So we're having the semiconducting devices, just like SCR, we're having a diode, we're having other devices like a BJT, right? MOSFET, etc. When the current flowing through the device increases, definitely its power loss increases. Power loss increases, so heat increases, right? Heat increases, right? So the meaning is the device temperature increases. Okay. Apart from that, conduction losses, we're having the switching losses also. Okay, and we're having a negligible blocking state losses also. Okay, so how these losses affects on the device? The meaning is how these losses are affecting the device by increasing the causing the power loss in terms of the heat, and due to that heat the temperature increases. Okay, so let me write power semiconductor devices having, yes, which losses we're having? Switching losses, second conducting losses or the conduction loss, and third one is the blocking state loss. It is a very small, okay, small blocking state loss. So due to these losses, yes, the power loss is taking place. Actually, what is the meaning of these losses? The resultant is a effect is a power loss is taking place, right? So power loss. Due to this power loss, the heat will be generated. Heat, right? Generation. And due to this heat, yes, the device temperature increases. Device temperature increases. Now in this section, we are going to model, okay, this process, okay, in one electrical circuit, and that is known as the thermal modeling of the SCR. Okay, thermal modeling of a SCR. So if you check, we're having a electrical circuit and at the right hand side we are having the thermal circuit. That is the analogy between electrical and the thermal. Okay. So, in electrical circuit, we are having the charge. Okay. Analogous of the charge in the thermal circuit, we are having the heat. Okay, heat. Unit of charge is coulomb. Unit of heat is joules. Right, joules. Second, we are having in electrical circuit current. That is the rate of flow of charges, na, right? Or rate of change of rate of flow of charge, dq by dt. Okay, so we are having a current which is equal to dq by dt. Analogous to this, in thermal circuit, we are having the heat transfer. Okay, heat transfer. That is rate of heat transfer. That is nothing but the thermal power. It is known as a thermal power, which is equal to rate of heat transfer. Heat transfer. You can check in electrical, we are having a dq by dt, na? So I is equal to dq by dt. Here we are having the thermal power is equal to d by dt of this heat transfer. D by dt of this heat transfer. Right. Third, in electrical circuit, we are having a voltage or the potential difference. Voltage or the potential difference. Okay, or potential difference. And in thermal circuit, we are having its analogous is temperature or the temperature difference. Temperature or the temperature difference. And the last one, in electrical circuit, we are having the resistance. And in thermal analogy, we are having, it is a thermal resistance. Thermal resistance. It is denoted with the theta. This one is denoted with R. This is denoted with voltage V. Okay. So temperature is denoted with the T. Okay. And what is the unit of temperature? In degree Celsius, right? So it is in degree Celsius. In degree Celsius. Okay. Next. What is the resistance? Resistance is equal to voltage divided by current, na? So here we are having, yes, here we are having thermal resistance theta is equal to what is the analogous of voltage in a thermal system or the thermal circuit. We are having a analogous of voltage is a temperature. Okay, so it is a temperature or the change in temperature, you can say, right, divided by current. What is the analogous to the current in a thermal system, the thermal circuit? We are having a thermal power. Okay, so it is a thermal power. Unit of thermal power is watt. Okay, right? So you can check here the unit of theta. Therefore, unit of theta is degree Celsius per watt. In some of the examinations, they have asked the question, unit of thermal resistance is, it is a degree Celsius per watt, because it is a temperature divided by your power, thermal power. So it is a degree Celsius per watt. Okay, so we're having the analogy between electrical circuit and thermal circuit. In the electrical circuit, we're having the charge, its equivalent or the analogous in the thermal circuit, we're having the heat. In electrical circuit, we are having the current, that is dq by dt. In a thermal circuit, we are having the thermal power. Okay, or it is also known as a heat power. It is also known as a heat power also. Okay, which is equal to rate of change of heat. That is nothing but the rate of heat transfer. In an electrical circuit, we are having a voltage or potential difference. Potential difference is nothing but the difference between the two voltages, na, two potentials, or you can see the two voltages. Similarly, we are having the temperature or the temperature difference. Unit of temperature is degree Celsius. In the electrical circuit, we are having a resistance. Its analogous in thermal circuit is a thermal resistance. Okay, so R and theta. Now, with the help of this analogy, okay, and how the actual heat transfer takes place in the device. Okay, from these 2 points, we are going to draw the circuit. Okay, and that is the thermal modeling. So let me first show you how the semiconductor devices are mounted, okay, or how these devices are placed, okay, on a particular structure. So we're having, suppose we're having the body of the device, that is the where actually the charges flow takes place, okay. So it is a device, we're having the junctions, right? Suppose we are having it as the SCR, P, N, P, and N. Okay. So it is like in between the layers, we are having a junction. This is the actual device where the charges flow is taking place. Okay. Next, basically this device is mounted on a casing. Okay. Right. So casing means it is like we are having a support, okay, structure, and on which we have mounted a device, actual device. Okay. So this is a case. Next, we are having a heat sink. We are using a heat sink. Okay. Why the heat sink is used? To control the temperature of the device, right? And last one, this is the heat sink. Okay. So this is the heat sink. And next we're having the ambient temperature, that is the surrounding temperature. Okay. So you can check when the current flows through the device. Suppose device is in a conduction mode, okay, and the current is flowing through the device. So current is flowing through the device, the meaning is actually the charges are moving there. Okay. So highest heat will be observed, or the highest temperature will be observed, okay, at the junction of the device, because the power loss is taking place into the device structure only na, and this is the where on the structure of the device. Okay. So highest temperature will be observed, because what is the result of that heat? Due to the heat, temperature is increasing na, right? So the highest temperature will be observed at the junction of the device, at the junction of the device. So let us consider this junction temperature is a Tj. Junction temperature is a Tj. Tj means the junction temperature, where you can experience the highest temperature, right? Next, now compared to the junction where the temperature of the case will be lesser, or it will be same? Definitely it will be somewhat lesser. Okay, because actual body of the device here we will be getting a highest temperature, and after that from junction towards, or from the device body towards the casing, okay, there will be, you can check, suppose the heat is generated, then that heat from one point to the other point, whether the same heat is transferred, no, no, right? So that's why, or the temperature is remains same, no. So that's why here the junction temperature will be higher. After that we will be getting somewhat lesser temperature, okay, at the casing. Compared to the casing, you will be getting the somewhat lesser temperature at the heat sink, because the purpose of the heat sink is to reduce the temperature of the device, okay, to reduce the temperature of the device. Okay. So that's why the temperature, or the temperature at the heat sink will be further lesser. Okay, it will be further lesser. So it is a Ts. And if you compare the temperature of the ambient, that is a Ta. This is the Ta. It will be, yes, again lesser than that of whatever the heat sink temperature. So here we are having, yes. So here we are having 4 nodes. One is a junction, second one is a case, third one is a heat sink, and fourth one is the ambient, where you can observe the different temperatures. Okay, different temperature. And what is the analogous of that temperature in electrical system? We are having a voltage na. So generally voltage we denote at a particular nodes. So similarly here in a modeling of the device, okay, what we are going to do? We are going to consider these nodes just like your temperatures. Okay, so temperatures are the Tj. Next one is the Tc. sink, and after that we are having the ambient. Okay. Next, the difference between these two temperatures, okay, difference between the temperatures of these 2 points, that is a Tj and Tc, okay, will be taken care by this thermal resistance, that is a theta Jc. Next, theta Cs, theta Sa, and whatever the power loss is taking place, that will be indicated with a current, na? Analogous is current, so that will be your, yes, here it is a power loss P. Okay, here it is a power loss P, thermal power. Okay, so you can check, same, you can check, it is like a simple electrical circuit we are having, series electrical circuit. Instead of the voltages, now we are having the temperatures at the nodes. Instead of the electrical resistance, we are having a thermal resistance. Okay, instead of current, now we are having a thermal power. We are having a thermal power. Okay, now from this, yes, can we write the expression for the power loss? Okay, thermal power or the power loss is equal to, you can check here, consider this as a current only, consider this as a current only. Okay, so P is equal to what? Tj minus Tc. How we write the current in the electrical circuit? Difference between the voltages divided by the resistance. Na? So same here, P is equal to, we can write it as a Tj minus Tc divided by theta Jc. Right? Further, we can write it as a difference between these two temperatures divided by this theta Cs. So it is a Tc minus Ts divided by theta Cs. Further, we can write it as a Ts minus Ta divided by theta Sa. You can check, this is a series circuit, na? Right? So whether the current that will be flowing here, okay, or the thermal power, okay, analogous of the current is a thermal power, that will be same, na? Because series circuit we are having. So that's why we can write is either potential difference or the temperature difference between these two nodes divided by this thermal resistance, potential difference between these two nodes divided by thermal resistance, potential difference between these two nodes divided by thermal resistance, or how we can write, or we can write it as which is equal to, right, same, all these expressions are valid. Okay, so which is equal to, can we write it as potential difference between this terminal and this terminal, that is the temperature difference, Tj minus Ts divided by addition of these two resistors, it is a theta Jc plus theta Cs, right? So Tj minus Ts divided by theta Jc plus theta Cs, again which is equal to, can we write it as Tc minus Ta divided by addition of these two thermal resistors, Tc minus Ta divided by theta Cs plus theta Sc. Okay, Tc minus Ta divided by theta Cs plus theta Sa. Further, can we write it as which is equal to this temperature minus this temperature, that is a Tj minus Ta divided by addition of all these thermal resistors. Yes, okay, so Tj minus Ta divided by theta Jc plus theta Cs plus theta Sa. All these are the valid expressions of your thermal power. All these are the valid expressions of your power loss, you can say. Okay, heat loss. Is this clear? Now where, let me write, where Tj, Tc, Ts and Ta, these are the temperatures, okay, at junction, case, sink and ambient respectively, ambient, okay, in degrees Celsius. What about the theta Jc? It is a thermal resistance between junction and case. What is the unit of thermal resistance? Degrees Celsius per watt. Okay, in degrees Celsius per watt. Theta Cs, it is a thermal resistance between case and sink. Sink is nothing but heat sink. Heat sink. So in again degree Celsius per watt. Theta SA. It is a thermal resistance between sink and ambient. Sink and ambient in again degree Celsius per watt. Okay. So theta JC, theta CS, and theta AC were having. Okay. And what is the P? P is a heat loss. Heat loss, or you can write the thermal power. Okay. In watt. In watt. Right. So this circuit indicates your thermal modeling. Okay. Of our SCR. Right. So this is having a relation with how the losses, due to the losses, whatever the heat is generated, okay, and whatever the power loss is taking place due to that, okay, that represents with this modeling. It is known as a thermal modeling. And important thing, only this circuit you need to understand. No need to memorize even. Okay, simply understand it. And once you understand this circuit, these expressions you can write. Okay, just like your in case of electrical circuit, current is nothing but voltage difference divided by resistance. Na? So here we are having a analogous to the current in a thermal system. We are having a thermal power. So P is equal to temperature difference. Instead of voltage difference, we will be having the temperature difference divided by thermal resistance, right? Like this. So they have asked the simple questions based on this. Okay. Next. So let us discuss the numericals. Yes. A thyristor is rated to carry full load current with an allowable case temperature of 100 degrees Celsius. Okay, means case temperature TC they have given 100 degrees Celsius for a maximum allowable junction temperature of 125 degrees Celsius. TJ junction temperature is given, and thermal resistance between case and ambient, that is a theta S, theta CA they have given. Thermal resistance between case and ambient. Okay, but between case and ambient we are having the sink also, na, right? So it is 0.5 degrees Celsius per watt. Find the sink temperature for an ambient temperature of 40 degrees Celsius. Take thermal resistance between sink and ambient as 0.4 degrees Celsius per watt. Okay. So first of all, let us note the data. It is given that TC is equal to 100 degrees Celsius. TJ is equal to 125 degrees Celsius. Thermal resistance between case and ambient. Thermal resistance between case and ambient. If you check the thermal resistance between case and ambient, it is nothing but theta CS plus theta SA. Na? You can check the circuit, you will understand. We're having the nodes like junction, case, sink, and ambient. Okay, so theta CS plus theta SA is given 0.5 degrees Celsius per watt. Find the sink temperature, means TS we need to find. For an ambient temperature, TA they have given, it is a 40 degrees Celsius. Take the thermal resistance between sink and ambient, means theta SA. They have given, it is a 0.4 degrees Celsius per watt. Okay. So now from this data, can we find the TS? You can check which things they have given. TC given, right? TA given, theta CS, theta SA given. So from TC minus TA divided by theta CS plus theta SA, can we find the power? Yes. Okay, and that power, thermal power, right, is again equal to, that will be remain same na, for TS minus TA upon theta SA. Let me draw the circuit, you will understand. Some students are worrying about the so today is it's the sixth day, I think, right? And still our first chapter is going on. Okay, whether can we complete the syllabus in the given time or time frame or not? Okay, don't worry, right? If requires, we'll be getting the additional days, right? Additional sessions you will be getting, right? So don't worry about the syllabus coverage. And as long as your syllabus is considered, you can check we're having the 4 major chapters. That is the switching devices. Second one is the rectifier. These 2 chapters are very big chapters, and lot of contents are there in these 2 chapters specifically. If you compare DC to DC converter, it will take hardly 5 to 6 hours to complete the DC to DC converter, because in the DC to DC converter, we are having hardly 3 circuits. Okay, buck, boost, and buck boost circuits. Okay, and in addition, we are having some basic chopper circuits and the type A, B, C, D like circuits. Okay, so hardly 5 to 6 hours it requires to complete, and very easy chapter. Regarding the inverter, if you check, okay, inverter is having a good weightage, and also if you check the contents are also moderate there. Okay, so it will take around 12 to 14 hours to complete the inverter, right? So don't worry about the syllabus coverage. And after the inverter, we're having the AC voltage controller, right? That is nothing but your cyclo converter and that AC to AC converter circuit. Okay, and that can be covered hardly within 3 hours, last 3 hours, because very small chapter and comparatively weightage are also very less, right? So don't worry about the syllabus coverage. If you check these first 2 chapters, that is the switching devices and the rectifier, these 2 chapters requires, okay, minimum 36 to 40 hours to complete, right? So it is a theta JC, theta CS, and theta SA, right? Next, so now if you check the data, given data, from this data can we write P is equal to, we are having P is equal to, you can check TC they have given, TA they have given, and theta CS plus theta SA also given. Theta CS plus theta SA means this is theta CS, this is theta SA. So can we write P is equal to TC minus TA divided by this resistor? Yes, we can write. So therefore P is equal to TC minus TA divided by theta CS plus theta SA. So which is equal to, what is TC they have given? TC is equal to 100 and TA is 40. So 100 minus 40 divided by theta CS plus theta SA. Theta CS plus theta SA is 0.5. Okay, so it is a 0.5. So if you check, it is equal to 60 by 0.5. So that will be equal to 120 watts. This is a power P. Okay, heat loss you can say, or thermal power. It is a 120 watt. Now our task is to find TS. Our task is to find TS. Now can we write again P is equal to TS minus TA upon theta SA, right? So P is equal to, also P is equal to TS minus TA divided by theta SA. So therefore we can write P is given, we have calculated now 120 is equal to TS minus TA. TS we need to find. TS minus TA is 40 divided by theta SA, if you check, it is a 0.4. It is a 0.4. So from this we can find TS. So if you check, it is 120 into 0.4 plus 14, it is a 88 degrees Celsius, right? 88 degrees Celsius. Is this clear? So these type of numericals they have asked. Yes, we'll take a break here. After the break, we'll discuss one more numerical related to the thermal modeling. And after that, we'll be moving towards the gate characteristics, right? Protection of the SCR. And if possible, we'll discuss the series parallel operation of SCR. Okay. Yes. We'll start at 7:20. 7:20. Yes. Okay. Okay. Let us discuss next example. For a thyristor, maximum junction temperature is 125 degrees Celsius. Okay. The thermal resistance for the thyristor sink combination are theta JC 0.16 degrees Celsius per watt, theta CS 0.08 degrees Celsius per watt, and for a heat sink temperature of 70 degrees Celsius. Calculate the total average power loss in the thyristor sink combination. Total average power loss is nothing but your power loss only. In case heat sink temperature is brought down to 60 degrees Celsius by forced cooling, the percentage increase in the device rating. Okay, percent increase in the device rating they have asked, right? So let us first note the data. Right? Okay. So it is given that Tj is equal to 125 degrees Celsius. The thermal resistance for the thyristor sink combination in that theta JC 0.16 degrees Celsius per watt and theta CS is equal to 0.08 degrees Celsius per watt. Okay. For a heat sink temperature, that is a TS, is equal to 70 degrees Celsius. First bit is calculate the total average power. So for the first bit, we need to find the power P, and the second bit, in case the heat sink temperature is brought down to 60 degrees Celsius. So now TS2, let me write it as, is equal to 60 degrees Celsius. Then our task is to find percentage increase in the device rating. Percentage increase in device rating. Device rating. Okay, that we need to find. So let us first discuss the first bit. It is very simple. We need to find only power. Na? So you can check Tj is given, Ts is given, and we know theta Jc and theta Cs, right? So from that, can we find the power? Okay, so we can find power P is equal to Tj minus Ts divided by theta Jc plus theta Cs, na? Which is equal to 125 minus 70 divided by theta Jc plus theta Cs. Theta Jc is 0.16 plus 0.08. Okay, so if you check, it is equal to 125 minus 70 divided by 0.24. Okay, it will be 229.17 watt, right? This is a power loss actually. Next, second bit, in case the heat sink temperature is brought down to 60 degrees Celsius, means we have used the forced cooling method and we have reduced the heat sink temperature to 60 degrees Celsius. Okay, 60 degrees Celsius. Then what will the percentage increase in the device rating, that we need to find. Okay, so let us first find the power corresponding to the TS2, that is a 60 degrees Celsius. Okay, so second bit, power for TS2 is equal to 60 degrees Celsius. So what is the power of the heat loss? So therefore P is equal to Tj minus TS2 now. Okay, because this is a sink temperature, na, new sink temperature, right? So after the external cooling method, external cooling we use, or the forced cooling we use, and we have reduced the temperature of the sink to the 60 degree, right? So now we need to consider it as a 60 degree here, divided by theta Jc plus theta Cs. So it is equal to 125 minus 60 divided by this term 0.16 plus 0.08. So if you check, it is equal to 270.83 watt. This is a power, actually, heat loss, actually, we can say, okay, 270.83. This is a power, actually. Now our task is to find the percentage increase in the device rating. So generally, the device rating is nothing but your voltage rating and current rating. Okay. So how the voltage and the current is related with your power, that we need to find, right? So you can check. We know now power P is proportional to current square, because power loss is nothing but your, it is like a heat loss, na, that is equal to your I square R loss type thing. Okay, so it is proportional to I square, or we are having P is proportional to V square. So now from this can we write, therefore I is proportional to under root P, or we can write V is proportional to under root P, right? Means your device voltage or current is proportional to square root of the power, square root of the power. Now you can check, in the first case we are having a power P is 229.17. Let us consider in the second case the power, let me indicate it as a P2. Let me indicate it as a P2. Okay. So what is the percentage change in the device rating? So therefore, percent change in device rating means what? Percentage change in the device voltage rating or device current rating. Okay, so it indicates percent change in device voltage current rating. Are you getting the point? So what is the percent change we can write? So which is equal to, let me write it as a first, that is the power ut, it is a under root P minus under root P2. Okay, right? So under root P minus, in the first case it is under root P2 divided by under root P2 into 100, or you can write under root P2 minus under root P divided by under root P, because previously we had a P, na? So it is a P. Either you can write, here is a minus, here it is a plus. Okay, so which is equal to, you can write minus under root, what is the P? 229.17 plus under root 270.83 divided by under root P, 229.17 into 100. So if we simplify it, we'll be getting it as equal to under root 270.83 minus 229.17. Yes, 8.71. 8.71%. So this is your percentage change in device rating. Whether it will increase or decrease? Whether the rating will increase or decrease? Yes, V is proportional to under root power. Power has increased, na? Yes or no? Right? So therefore, yes, the rating will increase, right? It will increase. Are you getting the point? Okay. So here try to understand the percentage change in device rating means voltage rating and current rating specifically. Okay. Next. So this is about the thermal modeling of the SCR. In the cell practice questions, okay, you are having the level 1, level 2 questions. Try to simplify these questions based on the thermal modeling. Very simple questions we have given there. And also try to solve the numericals from previous GATE and ESE questions. Okay. Also, if possible, please check the civil services examinations papers also. Okay, CSE. Next, let us discuss the next bit. Gate characteristics of SCR. Gate characteristics of SCR. So there is nothing much to explain, because this characteristic is directly given in the data sheet, okay, by the manufacturer. So basic purpose of this characteristic is it gives the safer operating area for the gate cathode circuit of the SCR. Okay, safer operating area for the gate cathode circuit of the SCR. So let me write, it gives safer operating area, that is the SOA, for gate cathode circuit of SCR. Circuit of SCR. So in this we are having, yes, here it is a IG, that is a gate current, and here it is a VG. Okay, so we are having total 3 curves here and 4 constraints. Okay, 3 curves and 4 constraints. So if you check the device structure, we are having a PN device, right? PN, P1, N1 minus, P2 and N2. Here it is an anode, here it is a cathode, and here it is a gate. Actually, this characteristic is a plot between VG and IG. Okay, VG and IG. VG is nothing but the voltage across gate and cathode terminals of the SCR. IG is nothing but the current flowing through the gate terminal of the SCR. Okay, so specifically, if you check between gate and cathode, we are having only P and N type layer, na? So it is like only one PN junction we are having. Between gate and cathode, we are having only PN junction. So PN junction means it is like your diode, right? It is like your diode. So if you check in the diode, in case of diode, we are having the voltage versus current characteristic. How it is? It is a V versus current, and this characteristic is like this. Okay. Now in the gate cathode characteristic, what we have done, we have taken the current is along the X and the voltage is along the Y axis. Okay. So if I take current along the X axis and voltage along the Y axis, okay, then this characteristic will look like this. Okay. So this characteristic will be like this. This is the first curve. This is the second curve. Okay. Here it is the first curve. Here it is the second curve. What the first and second curves indicates? Okay. Curve 1 indicates the this curve is when the small possible values of VG are applied, are maintained across the gate cathode circuit. Okay. So curve 1 is for minimum. Curve 1 is for minimum value of, okay, values of VG applied to SCR or the gate cathode circuit. This will be directly given by the manufacturer. You can check the data sheet of the device. SCR. And curve 2 is maximum values of VG applied to gate cathode. Okay, not SCR, gate cathode. Gate cathode. Here it is also gate cathode should be there. So next, so we're having the two curves. One gives the, you can check corresponding to curve 1, where having the VG values are very small and IG can be very, IG range is it is changing from minimum to the maximum. Corresponding to the second curve, you can check the VG values are very the VG value range is very high, na? That is from minimum to the maximum value. Okay, so it is for minimum VG, this is for maximum VG. Next, apart from these two curves, there are 4 constraints. These 4 constraints are like First one is Ig mean. Ig mean means minimum gate current required to be circulated in the gate cathode circuit of the device in order to initiate the turn on of a device. If I keep Ig value less than the Ig mean, our device will not turn on at all. Are you getting the point, right? Ig max. Second one is the Ig max. Ig max. This is a maximum possible gate current that can be circulated in the gate cathode circuit. We cannot circulate the gate current greater than that of the Ig max in the circuit. Okay, otherwise our gate cathode circuit will get damaged. Okay, so Ig mean, Ig max. Similarly, we are having the Vg mean and Vg max. We are having the Vg mean and Vg max. Vg mean and Vg max, right? So this is the Vg and Vg max. Vg mean means minimum value of voltage between gate and cathode. Vg, please don't get confused. Vg means strictly here voltage between gate and cathode. Vg is the voltage across device terminals. It is not the external source. Please be careful. External source will be connecting. That will be your ES. Okay. But here Vg means the voltage between gate and cathode only. Okay. So here one is the Vg mean, that is the minimum voltage required between gate and cathode in order to initiate the turn on of a device. And Vg max, that is the maximum gate current, maximum gate voltage that can be maintained across gate and cathode. Okay. So if you check from this, if you take the, yes, so we'll be having whatever the region here, right? From here till this point and here. Okay. So it indicates your maximum gate power loss, maximum area under this curve, na? That will be your maximum gate power loss, right? Now, apart from this, we are having PG average also, PG average also, because you can check if I operate the gate cathode circuit corresponding to Vg max and Ig max, your power loss will be more, okay, and that may damage our device. So for that, we are having limit for the power also. We are having the limit for the power also, and that power is limit is nothing but your PG average, that is equal to your PG average, and it is indicated like this. This is your PG average. Okay, this is your PG average curve. This is a curve 3. Curve 3 is a PG average. PG average, average gate power dissipation. Now, the area we are having bounded between these 4 constraints, okay, bounded by these 4 constraints. This one, right? Next, upper limit for Vg, Ig. Okay, so like this area we're having, that area will give you the safer operating area for the Vg and Ig values. Safer operating area for the Vg and Ig values. Okay, so let me write here it as A, B, C, D, E, and F. Okay, this area A, B, C, D, E, F, A, it indicates your safer operating area. Okay, for your SCR's gate cathode circuit. Means in order to turn on the SCR, we need to select the VGIG in between this only. In between this only. Okay, if your VGIG will be yes outside of this window, okay, then your SCR will either get damaged or it will not turn on at all. Okay, either it will get damaged or it will be it will not turn on. Like this is the case. Okay, so now let us discuss how to find the operating point. How to find the operating point. So this is like A, B, C, D, E, F, A. Let me indicate A, B, C, D, E, F, A. A, B, C, D, E, F, A. This is nothing but SOA for gate cathode circuit. Gate cathode circuit. Next, Apart from this, the manufacturer specifies the VGIG curves of a device, VGIG curves of a device for different temperatures, just like this. Let us indicate it as a curve A, B, and C. Okay, these are the VG versus IG curves specified, given by the manufacturer, okay, of that particular device for the different temperatures. Let me write A, B, and C. Curves A, B, and C. These are the VG-IG curves, or the gate cathode, you can say VG-IG curves of SCR, of particular SCR, okay, at different temperatures. This will be given by manufacturer. This is the one thing. Next, now how to find the safer operating area? Safer operating area we have identified, but how to find the operating point, specific operating point? Okay, so for that we need to draw the load line. So how to draw the load line? Let us discuss. So here we are having this is the anode cathode gate, and this is the PNPN structure of the device. Now in the gate cathode circuit, what we are required to do? We need to connect the external source, and one series resistor should be there, right, in order to control the gate current. Yes or no? So we're having ES, and yes, this is a ES, and here it is a RES we are having. Okay. Next, now here for this circuit we need to draw the load line. So if we check this circuit, by using this circuit, how much maximum VG, okay, how much maximum VG we can achieve, okay, means how much maximum VG we can achieve by this circuit. You can check the VG will be maximum when IG is equal to 0. Simply first apply KVL to this loop. What is the KVL equation? KVL to the loop, we can get it as KVL to loop. It is a plus ES minus IG into RES minus VG na, is equal to 0. You can check. Plus ES minus IG RES minus VG is equal to 0. Okay. So this is a KVL equation we are having. Now with the help of this equation, now we need to check how much maximum VG we can get, okay, from this circuit, and how much maximum current we can circulate, okay, with this by using this circuit. So now in order to get the maximum VG, IG should be 0. You can check now. VG will be maximum when this drop will be 0 na. This drop will be 0 when IG is equal to 0. Okay, so you can check here. Yes, when IG is equal to 0, ampere, then we can write VG is equal to ES, and this is the maximum VG. We can achieve, okay, by using ES RES, that gate cathode circuit. And similarly, when yes, VG is equal to 0, volt, then whatever the current in the circuit, that will be your maximum current na, right? You can check here. IG is equal to what? ES minus VG divided by RES. In order to get the maximum current, your VG should be minimum, and minimum VG will be your 0. So therefore IG is equal to your ES by RES. This indicates your like a maximum possible current that can be circulated, okay, by our ES and RES, or the gate cathode circuit, and this is the maximum possible VG, that can be achieved. So therefore we need to mark these 2 points also on the VG-IG curve, okay, on the VG-IG axis. So VG will be equal to your ES, right? So let me show here. Yes, maximum VG that is equal to your ES. ES value will be maximum value that can be achieved, okay, by using that circuit is equal to ES. Okay. Next, maximum value of current that can be achieved is equal to your ES by RES. ES by RES. Now we need to, yes, draw a straight line. That is nothing but your load line. That is nothing but your load line. So let me draw the straight line from here till that point, right? So here to here. Okay. Now you can check whatever the points we are having, okay, on this load line, let me indicate this as a load line. Whatever the points we are having on this load line, and those are, yes, coming in this window, those are your safer operating points. And how to select the safer from that safer operating points means whatever the points we are having here now on this line, all these are the safer operating points, okay, for our gate cathode circuit. Now from because we are having the infinite points now in between these two, so how to select the one particular point? Now that depends on your VG and IG of your device. VG IG character curve of your device means whatever the given by the manufacturer. For example, suppose we are operating it at a temperature of, let us consider corresponding to this curve. Okay, then our operating point will be this point. This will be the operating point. If we are operating at a temperature of suppose curve corresponding to this curve A, then this will be our operating point. Okay, so it indicates your operating point either here, here, or here. Okay. So here only 3 curves I have indicated for the different temperatures. Okay. But if you check the actual data sheet, you will understand we'll be having the number of curves here for the different temperatures. Okay. So this is the gate cathode characteristic of a SCR. It is given by the manufacturer. It tells about the safer operating area. Okay. For the VG and IG values or the gate cathode circuit of our SCR. Right. Now, important thing. While selecting the specific operating point, yes, what we need to do, requirement is that VG and IG or that operating point should lie, yes, in this window only, in this window only. That operating point should lie on the load line. Is this clear? Right? So now let us discuss the numericals related to the gate characteristics, right? Very simple numericals they have asked. Now, before that, let us have a discussion on maximum gate power and the average gate power. Okay, so if you check or if you recall the theoretical discussion, what we have done regarding the gate triggering, okay, we know, once the SCR turns on by using the gate signal, after that, if we remove the gate signal, then also our SCR will continue into the on state. Okay, so important thing is, the gate current is required to be circulated for very small time interval. Yes or no? Right. So let me consider this is a gate pulse your T and this is a IG. Let me write it as a gate pulse here. This is a TP. This is like your IG. That is the magnitude of the gate current. Right. Next again here it will be T. At T again I will circulate the next gate pulse. And so on, right? This is our IG. Now from this, how to find the average gate power? PG average is equal to, we know the gate power is equal to product of VG into IG. Okay, it is a product of voltage and current. So PG average is equal to 1 by T. VG will be your constant voltage, na? VG will be your, because it is a potential, it is a voltage across gate and cathode terminals, and in the gate and cathode terminals we are having the junction, na, PN junction. Okay, so it is a 1 by T integration from 0 to TP. Actually it is a VG into IG. Okay, VG, or let me write it as first 0 to T, then we will divide it into the two intervals, right? 0 to T, it is a VG into IG into DT. This can be written as 1 by T integration from 0 to TP VG into, during 0 to TP, what is the IG? IG is capital IG, na? So it is a constant. It is a IG into DT plus integration from TP to T. Okay, TP to T. It is a VG. VG will be constant. It is a VG only. Okay, into current is 0 into DT. So now from this we can write which is equal to 1 by t into, it is like a integration over, because this integration will become 0 only. Okay, so integration over 0 to tp will remain there, vg into ig into dt. Now further we can write it as which is equal to vg into ig. It is a constant now, because ig is, it is the magnitude of the gate current, it is a constant here. Okay, so we can write it as vg into ig into, we can write it as a tp by t. What is this tp indicates? TP means the pulse width of the gate signal. Na? This TP means what? It is the pulse width of the gate signal. So TP divided by total time T is nothing but your, like, it is a duty cycle or the duty ratio. Let me write it as a duty cycle D into VG into IG. This is your PG average. And where D is, you might have come across this duty cycle D in a chopper circuit, okay, or the DC to DC converters. Okay, so is equal to TP by T, which is equal to duty cycle, or it is a duty ratio. Okay, duty cycle or a duty ratio. So further we can write it as, therefore PG average is equal to duty cycle D into, what is this, VG into IG. VG is the constant voltage and IG is the magnitude of the gate current. Na? So can we write it as VG into IG is nothing but maximum gate power loss, PG max into PG max. Means if we circulate the gate current constant, okay, of IG magnitude, then you will be getting the power consumption will be maximum. Okay, then that will be your PG max, which is equal to VG into IG. Okay, so PG max. So this expression is important, right? Next, now let us discuss the numericals related to the gate cathode characteristics. Yes. And SCR has VG IG characteristics as VG is equal to 1.5 plus 8 IG. It is given, okay, means instead of curve, they have given the relation between VG and IG. In certain application, the gate voltage consists of a rectangular pulses of 12 volt and of duration 50 microsecond. Means it is like a gate voltage, means it is like your ES they have given. ES is a 12 volt, okay, and it is having a duration 50 microsecond with a duty cycle of 0.2. Find the value of series resistor RG. Instead of RES, now they have given here as RG, to be inserted in the gate circuit to limit the peak power dissipation in the gate to be 5 watt. So PG max they have given 5 watt. Calculate the average power dissipation in gate circuit. Okay, right? So we need to find the average power dissipation. And the second thing is, yes, RG we need to find. So let me write first, VG is equal to 1.5 plus 8 into IG. Okay, 1.5 plus 8 into IG. This is the variable IG. Next, it is given ES gate voltage is a 12 volt. Next, duty cycle D is equal to 0.2 and the duration is equal to 50 into 10 to the power minus 6 seconds. Our task is to find the RG to limit the PG max is equal to 5 watt, right? Yes, to limit the peak power dissipation. So we need to find the RG in the first bit, question mark, and second bit we need to find the average power dissipation, that is a PG average. What is the PG average? PG average is equal to duty cycle into PG max, na? Just now we have written, right? So PG max we know, duty cycle they have given 0.2. So simply we can write the PG average, right? So we can write second bit, PG average is equal to duty cycle D into PG max is equal to 0.2 into 5. So if you check, it is equal to 1 watt. That will be equal to 1 watt. Now next we need to find the RG. RG. So for that circuit will be like this. We are having SCR here, anode of a SCR, right? Cathode of a SCR, and here it is a gate terminal. This resistor they have given it as a RG. Here it is a 12-volt supply. Okay, 12-volt supply, right? And this is a VG. This is a VG. This is a IG. This is a IG, right? So now our task is to find the RG. Our task is to find the RG. So you can check the data given. ES is 12 volt. ES is 12. They have given the expression for VG is equal to 1.5 plus 8 into IG, right? Now, what is the power loss? Can we write PG average is equal to VG into IG, right? So now you can check here VG is, we are having expression. If I multiply this with your IG, okay, with your IG, then we can write, let me write VG is equal to 1.5 plus 8 into IG. Now PG is equal to your VG into IG. So that can be written as is equal to PG is equal to, we can write it as a 1.5 plus 8 into IG, okay, into this IG as it is. So this can be written as 1.5 into IG plus 8 into IG square, na? That will be equal to your PG. And what is PG we have written? It is a 1 watt, right? It is a 1 watt PG average. So now from this we can write IG. Therefore IG, if we simplify it for IG, we can write it as that will be like minus B under root, right? So it is a minus 1.5 plus minus under root B square minus 4AC, na? B square minus 4AC, that is a 1.5 square minus 4 into 8 into C. What is the C? Yes, that is a minus 1 here. That will be equal to minus 1. Divided by 2 into A. 2 into 8, right? Yes or no? We can write this as 8 into IG square plus 1.5 into IG, okay, minus 1 is equal to 0, na? It is like AX square plus BX plus C, right? So ABC we can find, okay? So IG we can write yes. Okay, so it is a 0.7, right? 0.272 ampere. Okay, so this is the IG we are getting. Now what is the VG we can get? Put this IG in equation, in that equation, so we'll be getting VG. So therefore VG is equal to 1.5 plus 8 IG, na? 1.5 plus 8 into IG. So is equal to 1.5 plus 8 into 0.272. So you can check it is 8 into plus 1.5. 3.676, na? This is a VG. So VG we are having this volt. IG we got 0.272, right? Next, now our task is to find the RG. Okay, so what is the RG? RG is like this is 12 volt minus VG divided by IG, na? Ohm's law. Potential difference is equal to current into resistor. So what is the potential here? It is a 12 volt. Here potential is VG. So it is a 12 minus VG divided by IG. Okay, so RG is equal to, therefore RG is equal to 12 minus VG divided by IG. So if you check, it is equal to 12 minus 3.676 divided by IG is 0.272. So if you check, it is equal to 30.6 ohm. Okay, 30.6 ohm. This we need to this much of resistor is required in order to limit the maximum power of 5 watt. Some students are saying that, sir, here we need to take the PG max. No, right? PG max is like your maximum VG and into what is the IG, right? So PG average is related to your duty cycle. So when you take here PG average only, please be careful, right? That is average power loss, right? So this is about the gate characteristics. Now let us discuss the protection of SCR. Protection of SCR. So as long as the power electronic circuitry is considered, our switching devices plays a very important role, okay, in the in getting the output of that converter or in getting the output of our circuitry. Okay, what is the expected output? So that's why here we need to protect, or our power electronic converters are very power electronic switches are very important for getting the output. So that's why we need to protect our devices. Okay, so as long as SCR is considered, we need to protect it against over voltage, over current, right? High di by dt protection, okay, and high dv by dt protection. Apart from these, we need to protect the gate cathode circuit of the device also. Okay, so one by one, let us discuss which protections are required to be given and how we are providing the protection against the particular that parameter. Okay, so protection of SCR. Let us write first over voltage protection. Second, over current protection. Third, protection against high di by dt. And protection against high dv by dt. So these protections are required. Let us discuss why these protections are required and how to protect. Okay, so let us put the heading over voltage protection. Over voltage protection. Over voltage protection. So first thing is why the over voltage protection is required. Suppose if we are not protected our SCR against the over voltage, then what will happen? Yes. What will happen? Our SCR will get burned, our SCR will get damaged. What will happen? Because everything means just like if the overload is there, okay, for electrical engineering students, okay, they only think that that device or that particular thing will burn, but it is not like that. Over voltage are having the two types. Suppose over voltage is there, but the value of that over voltage is not very high, okay, then in that case the false triggering of the device will take place. Now, what is the false triggering? Let us understand. Okay, so to protect against false triggering. False triggering. False triggering means at this instant we are not interested in turning on of a SCR, but due to all of a sudden over voltage, our SCR is turning on. That is nothing but the false triggering. You can check, you can recall the turn on methods of the SCR. In the turn on methods of the SCR, we are having the very first method, that is the forward voltage triggering. Yes or no? What that forward voltage triggering indicates? If the forward voltage across the SCR is high, then our SCR will get turn on. Yes or no? That is the meaning of that forward voltage triggering. So suppose in the over voltage, suppose if the over voltage is there, okay, is occurring, and due to that over voltage, is there possibility of our device may get triggered? Yes, right? Because we know na, due to the high forward voltage, that junction J2 depletion layer is breaks down, okay, and due to that suddenly a large number of charge carriers will be flowing, okay, and the device will switch from, yes, blocking mode to the conduction mode, right? So that is nothing but the false triggering. So we need to protect it against the false triggering. Second thing, are you getting the point? False triggering means what? We are not interested in turning on a device at this instant, but due to that over voltage, our device is turning on. And due to the over voltage, how the device is turning on? Because we are having the very first method in the turn on of a device, that is nothing but your, yes, forward voltage triggering. Okay, so in order to avoid the false triggering, okay, we need to protect the device against over voltage. Second thing, suppose if the voltage level is very high, voltage is over voltage only, but if the voltage is very high, then it will cause our device to damage permanently. Okay, so two things we are having. If the voltage is very high, then device will get permanently damaged. To avoid, let me write, to protect against, not to avoid the false triggering, that will be the good. Okay, to avoid the false triggering. And second is, yes, to avoid false triggering. Second is to avoid permanent damage. Okay, damage to SCR. So for this, we need to protect the SCR against over voltage. Now, how to protect the SCR against over voltage? For that, we are using the varistor. Okay, the device named varistor. Varistor is used. What this varistor indicates? This term varistor is nothing but variable resistor only. Variable resistor. Varistor means variable resistor. Okay, and during the normal, generally this varistor, if I want to protect the SCR against over voltage, where this varistor we require to connect, whether in parallel or series. Yes, if I want to protect my SCR against the over voltage, whether that protecting device we need to connect series or parallel. Series or parallel, some are saying series, some are saying parallel. Always keep it in mind. For the voltage protection, we need to connect that device in parallel only. Always keep it in mind. You can check now. Generally we are having the circuit breaker or the fuses. These are for to protect against the high current. Okay, so current is actually flowing in series circuit, current is same na. So that's why if we want to protect the our circuitry against the over current, that fuse or circuit breaker is connected in series. This is for current protection, I'm saying. But for voltage protection, if we want to protect against the voltage, okay, over voltage, then we need to connect it again in parallel with the device only. No? If the varistor is connected in series, how that varistor can protect the SCR against the over voltage, right? So over voltage is appearing across the anode and cathode terminals of the SCR. Na? So that's why we need to connect the across anode and cathode terminals, we need to connect the varistor. Okay. So varistor is connected in parallel. Varistor is connected in parallel. Always keep it in mind in electrical science or electrical engineering. Okay. If we want to protect our device against the over voltage, okay, or you can say the yes, over voltage, then we need to connect the protecting device, okay, in parallel with our main device, right? So varistor required to be connected in parallel with SCR, right? With the SCR. Yes, varistor is having a symbol like this. This is a varistor. Right? This is a varistor. And varistor is a device which offers a very high impedance during normal working voltage. And if the voltage is greater than the normal working voltage, its impedance falls suddenly. Okay, so let me draw the impedance versus voltage characteristic of this varistor. This is a voltage and here it is a impedance. Okay, so suppose voltage is in a normal range, okay, normal working voltage range. So it is like this. It indicates this is like a forward voltage and it is a normal working range. Okay, so V normal. It is a reverse voltage and it is a V normal. Now, if the voltage is a normal, okay, so it is like our SCR is not having any problem now, right? If the voltage is across the SCR is less than that of its rating, then it is like we don't have any problem. Okay, SCR is not having any problem. Okay, so that's why our varistor will offer a very high impedance. Okay, so you can imagine if varistor is offering a very high impedance and that varistor is connected in parallel with a SCR, so you can replace that varistor with a high impedance. So during the normal working voltage, whether our varistor will consume any power? No, because due to the high impedance, current flowing through the varistor will be very less, na? So that's why the power consumed by the varistor is very less. Okay, so it is not like that our varistor will be like a burden on our system. No, right? So let me show. It is like a coming from infinity, right? It is a coming from infinity. And if the voltage becomes abnormal, then impedance falls suddenly. Okay, similarly here it is also, it is coming from infinity. It is coming from infinity, na? Means if the voltage range is normal, then the impedance offered by the varistor is infinite. So you can check, na, varistor we are connecting in parallel with the SCR. If the working if the working voltage is normal, if the voltage across the SCR is normal, then it is like yes, our varistor will not consume any current. Okay, will not consume any power, right? But if the voltage across SCR becomes high, at that time our varistor will suddenly, impedance of the varistor will suddenly decrease. So it is like varistor will provide a low impedance path. Okay, right, for whatever the current that is flowing. Okay, that will be producing. Okay, and that current will be flowing through your varistor. Okay, you can check SCR is there. Okay, and here we are having SCR is there, and in parallel we are having the varistor. SCR, if for the working voltages, for the high over voltage protection, whether SCR is required to be operate in a conduction mode or a off state or the blocking mode. During the over voltage protection, we need to consider where SCR is in a on state or off state. It should be in the off state, na? Because if SCR is in off state, then and only then the voltage across SCR will be non-zero, na? You can check if SCR is in a on state, how the over voltage will appear across the SCR, right? So we need to consider the blocking mode only. We need to consider the blocking mode only, right? So yes, so here we are having the varistor. Generally, it is connected in parallel with the SCR. So let me show you. It will be like this. If the voltage is abnormal, then this varistor will directly act as a short circuit, we can say, because the impedance is very low. This is a varistor. This is a varistor, right? So right, so if this is offering a very low impedance during the abnormal working voltage, so what will happen? The resultant voltage will decrease, na? Right? The resultant voltage will decrease. So that's why SCR will be protected. This is the one thing. The second protection is we are having the overcurrent protection. Overcurrent protection. Why SCR is required to be protected against the overcurrent? Yes, why the overcurrent protection is required? Overcurrent protection. Suppose a high current is flowing through the SCR. What will happen? If a high current is flowing through the SCR, what will happen? Due to the high current, high power loss will be taking place. Due to the high power loss, high heat will be generated. Due to the high heat, device will get damaged, na? So in order to avoid the permanent damage of the device, we need to protect it against overcurrent, right? To avoid permanent damage, okay, of SCR. We need to protect against over voltage, sorry, overcurrent. Next, how to protect SCR against overcurrent? So for that, FACLF, that is the fast acting current limiting fuses are used. Okay, fast acting current limiting fuse is used. Okay, FACLF is used. Okay, is used. You getting the point? FACLF is used. Now, whether we need to connect it in series or parallel, FACLF, it should be connected in series or parallel. It should be connected in series only. Yes or no? Right? Yes. Because whatever the current, that high current should flow through this fuse, na? So that's why it should be connected in series. So FACLF is connected in series with SCR. FACLF means what? It is a fast acting current limiting fuse. It is like a fuse only, right? How the fuse operates? Yes, operation of the fuse. You can check every fuse is having one current rating. If the current flowing through the fuse, yes, goes beyond that current rating, then what will happen? It will create an open circuit, na? Right? It will create an open circuit, just like the same thing. So it is connected in series. So we are having the FACLF. And here it is the SCR. SCR. Is this clear? SCR is connected in series with the FACLF. So this is the second thing. Next, the third one, protection against the high DI by dt. High DI by dt protection. So why the protection against high DI by dt is required? In order to avoid the permanent damage of the SCR, okay, due to the local hotspots, okay, due to the local hotspots. We'll discuss what is the meaning of local hotspots and those things, okay. So to avoid permanent damage due to local hotspots, right? So suppose we know SCR, it is a PNPN device. SCR is a PNPN device. So it is a P1, here it is a N1 minus P2 and N2, right? P1, N1 minus, yes, P2 and N2. Here it is a anode, here it is a cathode, and here it is a gate. Okay. Now, high DI by dt. What the DI by dt indicates? Rate of change of current with respect to time. Okay, rate of change of current with respect to time, right? So, current flowing through the SCR, it is a IA. Suppose we are having the initially SCR is in an off state. So definitely what will happen? There is the depletion layer present, right? So this type of structure we are having. This is a load resistor RL. Here it is a supply voltage VS, right? And here it is a IE. Now, gate current, suppose we are circulating in order to turn on the SCR. Okay. So this is a VES. We are having the ES here. So here it is a ES. This is a RES. This is a VG. and here it is a Ig. Here it is a Ig, right? So now, yes, initially SR is in a off state, right? So it is like a junction J1, J2, J3, depletion layers are present, right? Now, in order to turn on the SCR, okay, so if we apply the forward voltage, it is like a junction J1 forward bias, junction J3 forward bias, junction J2 reverse bias. So it is in a forward bias mode, it is in a reverse bias mode, it is in a forward bias mode, right? Next, suppose the width of the depletion layers across junction J1, J3 are decreasing. So it is like we don't have any problem, okay? But the width of the depletion layer across junction J2 is non-zero. So it is like a plus here, positive charges will be here. And here we'll be having a negative charges at this side, right? If we further increase the voltage, yes, this width becomes zero. So it is like a short circuit. This will be like a short circuit, but this width is still increasing. So in order to turn on the device at a reduced voltage level, what we are doing, we are circulating the gate current. Okay. So now you can check when we circulate the gate current. Okay. When we circulate the gate current in the gate cathode circuit, it is like we are injecting the positive charges into the inner P2 layer. So if we are injecting the positive charges into the inner P2 layer, so suppose here we are injecting the positive charges. So positive charges are injecting from this point now. So as soon as the positive charge will inject here, these positive charges will be getting recombining and the neutralized. Okay. Whatever the negative charges are present near to this point, yes or no? Suppose the positive charges are injecting here. So first of all, these positive charges will be getting neutralized with whatever the negative charges are, yes, near to this gate terminal. Are you getting the point, right? So that's why suppose if first of all this region, these region charges are getting neutralized. So it is like if it is like this junction is already acting as a short circuit, this junction is already acting as a short circuit. So it is like whatever the current, okay, that will be flowing, okay, from anode to cathode, that current or those charges will be having the one small gate open in this region. Are you getting the point? Because when I inject the positive charges into the inner P2 layer, these positive charges will be getting neutralized with the negative charges. So compared to whatever the negative charges, those are present at the right hand side of the P2 layer. First of all, which negative charges will be getting neutralized? Whatever the negative charges, those are present at the left hand side of the P2 layer, na? Right? Because positive charges are injecting from this side, na? So that's why it is like after neutralization, it is like for our device, we will be having the possible path for the current, for the conduction. And you can check here, we are having a high voltage here. These two junctions are already acting as a short circuit. Okay. So if this gate opens, means if these charges gets neutralized, so it is like a very high current will flow through this region only, na? So if a current, very high current will flow through this region, so it will be like the temperature of that spot, temperature of that region will increase, because large number of charge carriers are passing through that small channel. Okay. So that's why the temperature of that region increases, and that temperature increase is nothing but your hot spot. Compared to remaining points, compared to remaining structure of the device, this region is having a high temperature. That's why it is a hot spot. And if that temperature is increases beyond one specific limit, okay, then our device will get damaged permanently. Are you getting the point? So in order to avoid that, yes, we need to protect it against the high di by dt. Why it is known as a di by dt? You can check. Initially current was only leakage current. As soon as I inject the positive charges, what will happen? These charges, whatever the charges, those are present near to the gate terminal. Whatever the negative charges, those are present near to the gate terminal. These charges will be getting neutralized, right? Recombining with the positive charges and getting neutralized. So that's why it is like for our charges, whatever the blocked charges were there, and whatever the charges, those were coming from the positive plate and the negative plate of the supply, for those charges, it is like we'll be having, those charges will be having a small channel will be there for the passing of the charges. Okay. And initially current was leakage current, and when that small channel opens, so suddenly very high current will flow now. So that is nothing but your di by dt. Current will increase, right, in a very short time interval. So that's why it is a di by dt. And due to that high current, okay, within a very short time, due to the high current, what is happening? That specific spots or that specific point temperature increases. That is nothing but your hot spot. That is nothing but the hot spot. Is this clear? Are you getting the point? Okay. So now how to protect the device against yes, local hotspot or against the high di by dt. So for that, whether in electrical engineering, in electrical science, we are having the element that opposes the change in the current. Yes, we are having the inductor, right? So we need to connect the inductor in series with the SCR. We need to connect the inductor in series with the SCR, right? So let me write inductor is connected. Inductor is connected in series with SCR, with the SCR. Are you getting the point? Inductor is required to be connected in series with the SCR. So it is like we're having a inductor and here it is a SCR. This inductor will oppose the sudden change in the current, right? So inductor and here it is SCR. Is this clear? So this is the di by dt, high di by dt protection. Next, protection against the high du by dt. High du by dt protection. Why the protection against high du by dt is required? Why the protection against high du by dt is required? Yes, to avoid the false triggering, right? By high du by dt triggering method. Yes, very good. So because in the turn on methods we are having the du by dt triggering, na? Right? So what is the that du by dt triggering? In a short time we are increasing the voltage by a very high amount, na? So it is like initially our SCR is in an off state. Junction J2 at upper side of the junction J2 we are having the positive charges, right? We are having the negative charges, and at the lower side we are having the positive charges kind of thing. So junction J2 will act as a capacitor, na? So current flowing through the capacitor, we wrote IC is equal to C into dV by dt. So if dV by dt increases, your current increases, right? In this way. So now high dV by dt protection to avoid false triggering. To avoid false triggering of the device, we need to protect it against high dV by dt. So how to protect SCR against high dV by dt? Whether we are having the element that opposes the change in the voltage. Yes, we are having a capacitor. Okay, so we can connect a capacitor. Okay, we can connect a capacitor. Capacitor is connected. Capacitor is connected in parallel with SCR, right? With the SCR. But only connection of the capacitor is not sufficient. Let us discuss why. Okay, so suppose we are having a SCR here and I have connected a capacitor here, right? This is a thyristor, let us consider T, and it is a capacitor. Suppose here we are using a load also. This voltage is DC voltage Vs. Okay, so now suppose we have connected a capacitor across the SCR, right? What is the purpose of function of the capacitor? To protect the SCR against the dV by dt. No problem. Our capacitor will 100% definitely protect our SCR against the dV by dt, because the basic function of the capacitor is it opposes the change in the voltage. Okay. Now, but the real thing is, suppose initially our thyristor is in an off state. Suppose initially this thyristor is in an off state. So thyristor is an open circuit. Okay. So if thyristor is in an off state, whether the current will flow from supply voltage, capacitor, load, and again back to the supply voltage. Yes, when thyristor is in off state, because whether thyristor we need to keep it in off state or on state, it depends on your circuit, na? Converters we are having, right? And that converter for getting the particular output, we need to yes, continuously turn on and turn off, turn on and turn off the thyristor. We need to maintain the thyristor in on state, off state, on state, off state, right? So suppose here when thyristor is in an off state, what is happening? Yes, it is like a current will flow from Vs, capacitor C, and the load in this loop, the current will flow. So it is like capacitor go on charging. Yes or no? Right? So to which voltage the capacitor will be getting charged? To which voltage the capacitor will be getting charged? Yes, this capacitor will be getting charged like a plus here, minus here. And to which voltage it will be getting charged? Yes, can anyone? When thyristor is in an off state, at which voltage the capacitor will be getting charged? Yes, it is equal to Vs volt only, right? It is equal to Vs volt only. We know now, because how to find what voltage the capacitor is getting charged? Simply remove this capacitor and check whatever the potential difference between those 2 points. Okay, so capacitor will be getting charged to the voltage of Vs volt. Now suppose this is when our SCR is in an off state, capacitor has charged. Now suppose we have turned on the SCR, we need to turn on the SCR. So suppose now I am turning on the SCR by using the gate signal. So as soon as I turn on the SCR, what will happen? This capacitor go on discharging into this loop now. So can you imagine here, the voltage across capacitor is very high now. It is a supply voltage. Capacitor has charged to the voltage of supply voltage. And when the thyristor turns on, this capacitor will discharge into this loop. So what is that discharging current of the capacitor? That capacitor discharging current is very high now. Because in this loop, if you check, we don't have any other element to limit the discharging current. We're having only capacitor. That too, it has charged to the high voltage of supply voltage. Okay, which is equal to supply voltage. So that's why a very high discharging current will flow through the circuit. And now important thing, this discharging current is flowing through the thyristor now. So you can check through the thyristor, once thyristor turns on, right? Through the thyristor, this high discharging current will flow. And due to that high discharging current, our thyristor will get damaged. Our thyristor will get damaged. Are you getting the point? So for that, in order to limit the discharging current of the capacitor, we need to connect the current limiting resistor, okay, in series with that capacitor. Means only connection of the capacitor is not sufficient. Capacitor will definitely protect against the dV by dt. But the disadvantage is when thyristor is in an off state, capacitor will be getting charged. And when thyristor turns on, this capacitor will discharge through this loop. Na? So when capacitor discharges through this loop, the high current will flow through the thyristor. And that high current will damage our thyristor. Are you getting the point? Is this clear? Right? Because we have connected the FACLF at this side now. Here we have connected the FACLF, fast acting current limiting switches. We have not connected here. Right? So please keep it in mind. So that's why a series resistor is required to be connected. Let me write here. Yes. Here resistor R is required to be connected. Okay. What is the function of this resistor R? To limit the discharging current of the capacitor. Okay. So capacitor is connected in parallel with the SCR. Let me write only connecting capacitor. Only connecting capacitor will protect SCR. Will protect SCR against high dV by dt. High dV by dt. But when SCR turns on, high discharging current of capacitor will flow through it, on SCR. And this high current may damage SCR permanently. Right? So therefore, a register is connected. Therefore, register is connected in series with SCR. In series with SCR. Okay. So that register in series with capacitor, not SCR, in series with capacitor. Right. So here in series with capacitor. Correct. So it is like this type of circuit will be getting. This is a C and this is a R. And here across it we are having a SCR, na? This type of circuit. And at this side we are having a supply and a load. Okay. So now this RC is known as a snubber circuit. This RC circuit is known as a snubber circuit. Okay. This is a snubber circuit. RC is known as a snubber circuit. Right. Now, what is the function of resistor? To limit the discharging current of the capacitor. Right. Function of resistor. Function of R is to limit discharging current. To limit discharging current of capacitor. Discharging current of a capacitor, right? Discharging current of capacitor. Okay. So only capacitor connection is not sufficient. We need to connect a resistor also. We need to connect a resistor also, right? So RC snubber circuit. Next. Now this is about the connection protection of the SCR. Okay. Now apart from the SCR protection, we need to protect the gate cathode circuit also. We need to protect the gate cathode circuit also. So let us discuss gate cathode protection. Gate cathode circuit protection. Gate cathode circuit protection. Yes. So gate cathode circuit, because you can check in the SCR we are having the two circuits. One is the across anode and cathode. Second one is across gate and cathode. Gate and cathode circuit is a low voltage, low current circuit. Anode cathode circuit is your load circuit, na? So it is having a high voltage and high current rating. Okay. So that's why your gate cathode circuit is a very sensitive, because it is having a less voltage and less current values. Okay. So that's why it is a very sensitive. And that is very important, na? Because in order to turn on the SCR, right, we are using that circuit, gate cathode circuit. Okay. So in the gate cathode circuit, we need to protect it against, first protection is over voltage. Over voltage protection. Second is over current protection. Over current protection. And third one is protection against the noise signal. Protection against noise signal. Noise signal. Okay. So let us discuss one by one. First one is the over voltage protection. Over voltage protection. Over voltage protection. Due to the over voltage, what will happen? If your voltage will be greater than, suppose we are having the for Vg we are having the limit, na, Vg min and Vg max, right? So if the voltage is greater than the Vg max, what will happen? It will damage your gate cathode circuit, okay, or the gate cathode junction. So that's why we need to protect it against the over voltage, okay, to avoid damage to gate cathode junction or gate cathode circuit. Okay. How to protect it? Here we need not to connect the varistor, okay, because in anode cathode circuit, in the SCR case, whatever the varistor we used, that was the high voltage, okay, right, because their over voltage was the very high. Here the over voltage range is very less. So that's why generally a Zener diode is connected. A Zener is connected. You might have heard the Zener as a voltage regulator. Okay, so we can connect the Zener. So Zener diode is used. Zener diode is used. Right. Second, overcurrent protection. Overcurrent protection. Yes. Yes, overcurrent protection. Why it is required? Because here current is nothing but your gate current. Okay. So again, overcurrent, due to the overcurrent, what happens? Either your device will get false triggered. Okay. Or if the current is very high, then it will your gate cathode circuit may get damaged. Okay. So to avoid false triggering, or damage to gate cathode circuit, we need to protect it against overcurrent, right? How to protect against the overcurrent? So in that case, we can use a small resistor. Okay, small resistor is connected. Small resistor is connected in series. In series. I will show you the all together diagram, right? And third one is the protection against the noise signal. Protection against the noise signal. Yes. Why the protection against the noise signal is required? You can check. Due to the surrounding noise, there is a possibility of induced EMF into our gate cathode circuit, and due to those induced EMF, okay, our device may get false triggered. Okay, so to avoid that false triggering, we need to protect it against the noise signal. Okay, to avoid false triggering. How to protect? Yes, against the noise signal. What is the difference between your noise signal and whatever our power signals are having? Noise signal is having a very high frequency. If you check, okay, so that's why here we can use the RC filter. I will explain how this RC filter will help. Okay, RC filter is used. So you can check the all together the protection diagram of our SCR is, it will be like this. Here we are having a FACLF. Next, we are having an inductor. Next, here we are having a SCR. Okay. Here we are having a RC number. Next. Yes, definitely the varistor we need to connect. This is a varistor. Okay, this is a snubber. This is a L FACLF, right? And in gate and cathode, we are having, yes, this is a gate terminal. Here it is a cathode terminal. Yes. We need to connect a small resistor in series. Here it is a Zener. It's connected, right? Zener as an voltage regulator. Okay. Next, here it is a R, and here it is a C. This is RC filter. This is a small resistor. This is a RF, CF, let me write. And here it is a ZD, Zener diode. So we are having very small device actually, but you can check the protection diagram, right? Apart from this, we need to add heat sink also in order to limit the temperature, okay, of the device. HES, right? So HES, this is a heat sink. Right now, let us discuss how this Zener diode or the gate cathode protection. Okay, so this Zener diode is having some rating, okay, voltage rating. If that voltage, if the voltage across that Zener diode is becomes greater than that, whatever its voltage, okay, that Zener diode will maintain the voltage which is equal to its rated voltage only. Okay, if the voltage is less than that of its rated voltage, means between these 2 points, if the voltage is less than that of the voltage rating of the Zener diode, then the Zener diode will give the voltage as it is, whatever the less value, actual value is there. But if the voltage between these 2 points is greater than the voltage rating of this Zener diode, then what the voltage then what the Zener diode will do? Zener diode will, yes, give the output as a whatever the voltage rating of the Zener diode. Okay, so that's why it will protect it against the over voltage. Second thing, over current, this resistor we are using here, okay, to limit the current in, that is the gate current. Third, we are having the RF and CF. You can check. Basically, this protection is to protect against the noise signal. The frequency of the noise signal is high. So for the high frequency, what about the impedance or the, yes, impedance offered by the capacitor? For the high frequency, the impedance offered by the capacitor, okay, it will be very less. Na? It is 1 by omega c. If frequency is high, then 1 by omega c, that is the XC, will be very less. If XC is less, means what? This capacitor will act as a short circuit. Are you getting the point? Means whatever the noise signals are coming here, these signals will be directly, yes, passing through this short circuit branch. These signals will not go towards, okay, this gate terminal or the gate cathode terminals. Are you getting the point? So that's why this capacitor is very important. But suppose in the noise signal, we don't know the frequency. There will be some mixed frequency also, right? So if the frequency is not that much high, then this resistor, okay, will attenuate, okay, will decrease the strength of that noise signal. How? Means whatever the EMF is induced due to the noise signal, okay, due to that induced EMF, this small resistor will provide the path here, okay, through this RF, so that the effect of that noise signal will not be high, okay, for this gate and cathode terminals, right? So we are having RF and CF. Is this clear? So this is for over voltage, number is for high dV by dt, L is for high di by dt, FSLF is for high current, Zener diode is for over voltage in case of gate and cathode, R is for over current in case of gate cathode, REF and CF, these are for protection against the noise signal. HS is the heat sink to limit the temperature. Okay, so this is the overall protection diagram of a SCR. This is the SCR we are having. Okay, you can check how much protection we need to maintain, we need to apply for this SCR, because SCR or our switching devices are very important, okay, for our converter circuitries, right? If switching devices will not operate properly, your converter will not give the output whatever we expect, okay, desired output it will not give, right? So next, enough for today. Okay, we'll stop here. Tomorrow we'll discuss the numericals related to the protection of SCR and then series parallel operation. Okay, yes, if you are having any doubt, please ask. Yes, Manjunath.
Yes, sir. Sir, while finding I naught in current commutation at t equal to t3, the signal is of like ramp, no sir? How we took sinusoidal, sir?
Okay, I will explain. The ramp actually starts from T3, na? but till T3 we are having sinusoidal only. Just a minute, let me unmute all the participants. Where is them? Okay. In the current commutation, na?
Yes, sir.
Yes. Here. Yes, your doubt is from T3 till T5 we are having a ramp, right?
Yes, sir. But
From
we're
T from yes.
but we're finding current no, sir. I not.
Yes, that is what I am saying. Ramp is from T3 till T5, but between T1 till T3, what is the nature? Sinusoidal, na?
Yes, sir.
So that's why, because this T3 is like your sinusoidal's upper last limit, na? And from T3 means T3 is like a boundary for your sinusoidal and the ramp.
Sir, what about current across capacitor, sir?
Current across nahi, current flow hota hai. Current flowing.
Yes, sir. That current flowing through capacitor.
Yes, it is a sinusoidal only, na, till T3.
Sir, between T2 to T3, it is ramp or it is sinusoidal, sir?
It is a sinusoidal only. You can
Okay,
check. This is a from T1 till T3 we are having a co-sinusoidal voltage, and from T1 till T3 current is a sinusoidal only.
Understood, sir. Understood.
How the capacitor current can be the ramp? We are having capacitor current only sinusoidal and constant, and capacitor voltage is a co-sinusoidal and ramp, right?
Yes, sir.
Okay, good. Right. Next.
Hello, sir.
Hello,
sir.
please.
Hello, sir.
Yes, one by one.
Sir, in today's current computation, sir.
Current commutation.
Sir, during T0 to T1,
During T0 to
T1, sir,
okay 0 to T1, huh?
the capacitor can discharge through load, no, sir.
How? Will you please explain the path?
So through resistor T1 to load,
Okay,
sir.
you are saying capacitor is charged to plus here, minus here, left side plate positive, right side plate negative, right?
Yes, sir.
Okay, so how it can discharge? Please explain. C T1 next.
To load, sir. Diode.
Load and next.
Okay.
No, discharging path is not. Discharging path means what? If the current is coming out from the positive plate, na, the same current should come through the negative plate. Then and only then you can say the discharging is there. Yes or no?
Okay, sir.
Right? Okay.
Sir, one more. Sir, in power consumption, sir.
Yes.
Thermal modeling of SCR, sir.
Thermal modeling of SCR. Okay. Yes.
In some, sir.
In that?
In some, sir, in numerical 2.
Numerical 2 you are saying. Okay. Huh.
Sir, actually, you are saying that, sir, heat sink temperature is decreased or not, sir?
Heat sink temperature is decreased to 60 degrees. Yes.
Then power loss will decrease, no, sir, actually.
No, na. How the
Temperature.
temperature has decreased. Temperature has decreased, but temperature difference is increased, na.
Yes, sir. Yes, sir.
And your power loss is proportional to the temperature difference.
Okay. Sir, the second bit once explained, sir.
Second bit rating, na.
Yes, sir. Yes, sir.
Okay. No. See. Actually, the device rating is like a voltage rating and current rating. Okay.
Yes, sir.
And we know now power is proportional to your current square,
Yes, sir.
which is proportional to again I square, V square only, na.
Yes, sir.
So in that we can say I is proportional to square root P and V is proportional to square root P only. Right?
Okay. Understood.
And in this case, what I have done, this is a higher value minus lower value. Okay. Like this, we have calculated.
So you are converting into electrical rating. Change in
I am converting to
electrical rating. No, sir. Change in device rating means it is electrical rating.
change in device rating means that electrical rating only, voltage and current rating.
Okay.
Right? Okay.
Hello, sir.
Yes, please.
Can you open the first question, sir? First numerical after current commutation.
Current commutation first numerical. Yes, here it is.
You have said L is equal to 5 micro Henry. Can it be possible? So generally, that much low is it possible? Inductor value.
Yes, yes, it is possible,
Okay, okay.
right?
Yes, sir.
It is not like that inductor is only in milli Henry,
Okay, okay. Sir.
right? Yes,
Hello,
we can
sir.
connect. Yes,
And
Hello,
what
sir.
are local hotspots, sir?
local hotspot.
Yes, sir. In high DI by dt you have explained.
Yes, yes, yes. Protection, na?
Yes, sir.
Yes, yes. Here, the local hotspot means, yes, this diagram.
Yes,
Okay.
sir. Yes, sir.
Actually, hotspot means what? We are having one spot where the temperature will be more high. Yes or no? That's why it is a
Yes, sir.
hotspot.
Hot.
Now, you can check in a semiconductor device why the temperature will increase due to the high current,
Okay, sir.
right? And when we were turning on the device na SCR and we're injecting the positive charges here. So
Yes, sir.
at the
Neutralize at left side.
yes, left
Sir,
side it will
5
be
minutes,
getting neutralized, right?
Yes, sir.
So due to that, what is happening? Most of the charges will be flowing through this channel now, because
Yes, sir. Yes, sir.
this part is blocked only, right hand side part, and
Yes,
this
sir.
is a very small channel we are having. So that's why most of the charges will be passing through this. So that's
Yes,
why
sir.
the
Okay.
charges are passing. So that's why current will be very high.
Okay, okay.
That's
Yes,
why the
sir.
temperature will be more,
Yeah, okay,
right?
sir. Okay. Okay. Thank you, sir. That's it.
Hello, sir.
Yes. Next.
Hello, sir.
Yes, please.
Sir, what is the difference between dV by dt and voltage over voltage production, sir?
Okay. dV by dt and over voltage.
Yes, sir.
dV by dt means sudden change in a voltage within a short time,
Okay, sir.
and over voltage means voltage value is high. It doesn't have any relation with that your dt.
Sir, whether varistor itself is enough to protect from the over voltage, sir. Otherwise, any other device is required, sir.
I'm not getting clearly. Please, will you please explain? Please speak a bit louder.
Sir, in dV by dt, sir,
In dV by dt,
that varistor itself will protect, no, sir, from over voltage.
okay, means you are saying like that. Okay.
Why? What is the necessary of that circuit? Snubber, sir?
Varistor's function is to protect against over voltage.
Okay, sir.
If you check the dV by dt, your varistor is like a variable resistor.
Okay,
It
sir.
will not protect the SCR against the dV by dt.
Okay, sir.
For that, we need to go for the capacitor. That is a basic element only.
Okay, sir. The
The
varistor.
capacitor will not protect against the over voltage.
Okay, sir. Okay.
Capacitor will protect against that thing, dV by dt only.
Okay, sir. Okay. Sir, the varistor will not provide protection against sudden change, no, sir.
Yes, it will not change. It will not protect against certain change.
Okay,
If
sir.
the voltage is, now you can check. Now suppose we are having, suppose the voltage is in a normal working voltage only range. Okay. Then what is happening in the normal working voltage? Suppose we are having a SCR. It is having a voltage rating of, let us consider 500 volt. Okay.
Okay, sir. Okay,
And
sir.
suppose the voltage is suddenly changing from 0 volt to the 500 volt in a very short time interval, in microsecond, let us consider.
Okay, sir.
Whether your varistor will protect,
No, sir.
because 500 volt is like a normal working for varistor.
Okay, sir.
So your varistor will not protect your SCR, right?
Okay, sir. Okay, sir. I understood, sir.
For,
Sir,
for abnormal voltages, you can say yes, varistor can help, right?
okay, sir.
Right. Okay. Yes.
Sir, one doubt, sir.
Yes.
Sir, the numerical before you take protection of SCR, sir.
Numerical before protection. That is the gate characteristics.
Yes, sir.
Yes.
Sir, in that how, sir, we have taken for RG, P average is equal to VG into IG, sir. It should be P max only, no, sir.
What you are saying?
Sir, you already explained,
Yes,
sir.
you are
that,
saying here it is. You
yes,
are
sir.
saying this
it
should be
should-
PG max.
yes, sir. Why it came P average, sir?
No, actually the thing is, if you check the gate characteristics of the SCR,
Oh,
right?
sir.
We are having a limit for the gate power till PG average only, na?
Yes, sir.
And what about here? Whatever the VG and IG we have calculated here, right? Whether this VG and IG we require, those should belong to that window or outside the window.
It should be within that window.
Belong
Sir.
to window. So belong to
Ah.
window means we need to consider PG average only, na?
Yes, sir.
Right?
Yes, sir. Okay, sir. Okay, sir. Thank you, sir.
Yeah. Yes, next.
Hello, sir.
Yes, please.
Hello.
Yes, please.
Sir, in current commutation, once explain the direction of capacitors at T is equal to T2.
In current commutation, yes.
Direction of capacitors.
Capacitor current
Capacitor at T is equal to 2.
at T is equal to
T2.
T2.
Of that.
Okay. At T is equal to T2, what do you want? Polarity of the voltage. of the capacitor?
Yes, sir. Yes, sir. Once that direction.
The thing is, what is happening here? 0 to T1, if you check, capacitor is initially charged to plus here, minus here. 0 to T1, what is happening? Capacitor is not discharging at all. At T1, we are applying the gate pulse to auxiliary thyristor. So from T1 to T2, capacitor will discharge and again charge to the reverse polarity means what? Capacitor polarity will be plus here and minus here. Are you getting the point?
Yes, sir.
Hello?
Yes, sir.
Are you getting the point? At T is equal to T2, the polarity will be plus here, minus here, and the voltage is Vs only.
Okay, sir. But it discharges no, sir.
But how discharges?
Discharges no.
Okay, means from T2 to T3 you are saying. Right? So
Yes.
now what is happening in this circuit? You can check if capacitor voltage is like plus here, minus here. Okay, means here it is plus, here it is minus, this voltage is Vs. So this thyristor will be in the off state only because the reverse voltage. And the first thing is current flow in the thyristor has reached the zero value. Once this is in the off state, this capacitor will discharge through this loop. Right? And this diode will be in the conduction mode. So capacitor will discharges through this loop. So when capacitor discharges in this loop through the thyristor T1, we are having two currents. One is the I0 and second one is the discharging current of the capacitor. Right? And as time increases, your capacitor current increases, na? Right? So that's why you can check here, capacitor current is increasing and your IT1 is decreasing because it is the difference between I0 and IC. So that's why it is a decreasing. IC increasing, na? Is this clear?
Yes, sir.
And this will be till this instant only, till T3. Once at T3, once this capacitor discharging current reaches I0, na, then your thyristor current will become 0 and capacitor will discharge through the load now. So that's why we're having the constant current, right?
Yes, sir. Good evening, sir.
Yes, good evening.
Sir, in that LC circuit, third problem, sir. Can you once open that?
Third problem, LC circuit. Just a
P
minute.
greater than 0.
Just a minute. Current commutation. Current commutation, na?
Yes, sir. Yes, sir. After the current
Yes,
computation.
this polarity should be reversed, huh?
Can you explain one that's problem, sir? Because I'm not.
Okay, I will explain. Just a minute. Just a minute. My OneNote is having some problem. I will reshare it. Just a minute. Actually, OneNote is taking time.
Okay, sir.
Just wait.
Sir?
Yes, please.
Sir, what is the need of connecting inductor after capacitor, sir, in current computation?
Inductor after
In
capa-
series,
Hmm.
in series with capacitor, what is the need, sir? However, the capacitor current across flow through the reverse of the thyristor, no, sir. What is the need of inductor, sir?
Okay. You can check if you remove this inductor and when the auxiliary thyristor turns on, what will happen to the circuit? Whether your auxiliary thyristor will get damaged?
Sir.
You can check the circuit. Just a minute. OneNote, we don't know what is the problem. You can check the circuit. Actually, the problem is due to my OneNote is having a problem. I am unable to open that diagram. Okay. You can check the inductor is there. Okay. And if you remove the inductor and when your auxiliary thyristor is turned on, at
Yes,
that
sir.
time when capacitor discharges through the auxiliary thyristor, then what will happen? Suddenly very high current will flow through the auxiliary thyristor, and your auxiliary thyristor, yes, will get damaged, right? So that's why we'll to connect the inductor in order to oppose the change in the current, right?
Okay, sir. Okay.
Hello, good evening, sir.
Good evening.
Sir,
Sir,
could you tell the difference between the peak instantaneous power loss and the average power loss?
Peak instantaneous power loss means, suppose we're having a gate cathode circuit. Vg is constant. Okay, let us consider 10 volt, and
Okay.
Ig is also constant current. Suppose Ig is also constant current. Then what is the power loss in that case? That will be your maximum power loss. And
Right.
second thing is, suppose we're having a Ig is like a pulse waveform. Then in that case, whatever the power loss you are getting, right? That will be your average power loss, which is equal to D into Pg max. You can check Ig, you can consider the continuous current, and second thing, consider the Ig as a pulse. Pulse means for 0 to Tp, Ig is non-zero. Tp to T, Ig is 0, and again non-zero, again 0. Right? Am I audible?
Hi, yes, sir.
Okay.
Could
Hello,
you
sir.
write that? I understand.
Yes.
Good evening, sir.
Good evening.
Sir, in circuit, in current commutation, in circuit turn off time calculation, if current
In
is
current commutation
the circuit turn off time calculation,
circuit, yes, TC, yeah. Okay.
C into VAB by I naught, na sir.
C into VAB by not, right? Correct.
Voltage is reverse. Voltage is in negative and reverse direction. That time
VC is
VC,
negative. Yes, VC is
VC is
negative.
current is positive, na sir.
Current is positive.
But in that case, we are at time T equal to T3, IC is equal to I naught, na sir.
At T is equal to
T3,
T3, na?
IC equal to I naught.
Correct,
But IC is I na sir, because at time interval T2 to T3, the current is positive slope, na sir.
Yes.
But in calculation we are taking negative slope, na sir.
I am taking it as a
Negative slope minus Vs into root of C by L sin of omega naught T3 minus
okay.
T1
No,
I naught.
that angle we have considered from T1, na?
But we are
Whether we have considered that angle is omega 0 into, I think, T3 minus T1, na?
yes sir. But
So you
at
can
that time
check
I have
omega 0 into T3 minus, yes.
T3 minus T1 consideration, sir.
Yeah, omega 0 into T3 minus T1 angle is that is your like omega 0 into T2 minus T1 plus omega 0 into T3 minus T2.
But we are considering overall negative sign, na sir.
Yeah, overall means what? Suppose you can check. Suppose
But
I am
T3
having the waveform of minus Im sin of omega t. Let me discuss. Let me first explain. Suppose we are having a Im is equal to, we are having the I is equal to minus Im into sin of omega t. Okay.
Yes, sir.
So at omega t is equal to 270 degree.
Yes, sir.
If I want to find the value, then what I need to consider? It is like a Im into sin of 270 degree I need to put na.
Yes, sir. Yes.
And that 270 degree, whether it is starting from that, from where the waveform has started, at that is from t is equal to 0 na.
Okay,
So
okay,
here
I
we
can
have
understand.
considered from t1. Is this clear?
Yes, sir. Yes.
Right?
Sir, another doubt in gate triggering circuit,
Okay.
we have do one problem. Is equal to VG into IZ.
Huh.
That is maximum value, na, sir. But we are taking average value. But before calculation,
No,
we are
just no,
taken.
just,
But
no,
before
just know the same
calculation,
thing I explained it to. Yes, yes. Let me explain.
Okay.
Actually, the thing is, we need to find the VG and IG values. We need to limit the IG na.
yes, sir.
So we need to find the value of VG and IG that should belong to that gate cathode characteristic window, that is the Sapir operating area.
Safer operating. Yes, sir.
And for Sapir operating area, which power limit we are having? Whether it is a PG max or PG average.
PG average.
So that's why we need to consider the PG average na.
But before calculation, we are taken VG, IZ is not Pmax. Na.
No, that the second bit is there, and for that VG into capital IG means your that maximum gate power, right?
Yes, sir.
Okay. And second thing is whether the gate current we are having, okay, or the voltage they have given, right? Instead
In
of
terms
current, they
of
have
gate
given the
current
voltage.
relation, we have taken average power, na, sir.
Yes.
Okay, sir.
Okay. And
Okay.
always we need to keep the average only, yeah, because
Okay.
we require our VGIG, that is the operating point of the gate cathode circuit, that should belong to that Sapir operating area, na?
Yes, sir. Yes, sir.
And for Sapir operating area, we are having a limit at PG average.
Okay, I can understand.
Right? Okay.
Okay. Thank you.
Okay. Actually, my OneNote is not, I don't know whether the screen is visible to you or not.
No, sir.
No, na. Actually, it is showing, we are sorry, OneNote is cleaning up from the last time it was open, and it is taking the time. And the thing is, if I want to restart that OneNote, I need to restart my system actually. If I restart the system,
problem.
then it is actually the meeting time is over, na. So that's
Yes,
why
sir.
again I cannot start the meeting. That is the issue.
Okay.
Anyways, you can ask your doubts. Okay.
Thank you, sir.
Yes. Okay. Next.
Hello, sir.
Yes, please.
Sir, in that linked problem that we did, we like for the thyristor to turn off, we took the time assuming that when the current becomes 0, the thyristor would turn off, right?
Just please explain once.
Sir, in that linked problem that we did, we were asked to find the time at which the thyristor would turn off.
Find the time at which yes, the thyristor will turn off.
Yeah.
Yes.
For that, we assume that when the current becomes 0, the thyristor would turn off, and we calculated the time based on that.
Correct.
Sir, but like earlier we discussed that even if the current becomes 0, then for some time that the charges would have to be removed and the depletion layer should be formed, right?
I got your doubt. Please listen.
Yeah.
The thing is, very first requirement for the commutation, that is a turning off of a thyristor, is anode current should be less than the holding current. Yes or no? In theoretical case, we consider it as a 0 ampere, right?
Okay. Yeah.
Second thing, so as soon as your current becomes 0, your thyristor will 100% acts as an open circuit. It will turn off only. Next, but the thing is, if the reverse voltage is not maintained across the thyristor now for the sufficient time means for the time which is greater than or equal to TQ, then again your thyristor will come back, means that thyristor will not successfully turn off. That is the thing. But if you check here, whether the current becomes zero at that instant, your thyristor is turning off or not, it is turning off only. But whether it is successfully turning off or not, it depends on that reverse voltage.
Okay, sir. So,
So while
like,
solving the numericals, okay, always keep it in mind. We need to consider the instant at which t is equal to 0 na. At
Okay,
that
sir.
instant, your thyristor is turning off. Means at which the current becomes 0 na. The instant at which current becomes 0. That instant we need to consider the thyristor has turned off. Means we are assuming that the reverse voltage will be maintained, because they have not discussed anything. They have not commented anything na, regarding your circuit turn off time and for how much time the reverse voltage is maintained. Means
Yes,
indirectly
sir.
what they, yes, we need to assume here ki they have maintained the reverse voltage for a sufficient time.
Okay,
Right?
sir. Okay, sir.
Okay.
Sir, then one more thing that,
Yes.
like, this is a general doubt. Like, usually in devices, when we have a heat sink that we
Will you
place.
please speak a bit louder, please?
Sir, is it better now?
Yes, better now.
Sir, like, this is a general doubt. Like, usually in devices having heat sink, we place fans and all to circulate the air so that the temperature is reduced faster, right?
Okay.
So in the problem that we did, when the temperature is lowered, actually the power loss increased. So that doesn't seem to make sense to me. So how
Means
that,
when the temperature decreases, then
like in the problem that we did, when the temperature was decreased, the power loss actually increased, right?
no, actually the thing is the sink temperature decreased.
Yeah, heat sink
But-
temperature.
Yes. And but temperature difference is increased, na?
Yes, sir. Yeah.
That is the issue. Means anyway, our main task is, our main motto is to limit the junction temperature, because the highest temperature will be at the junction, na?
Correct.
Suppose if by any means if I decrease the junction temperature, then definitely your power loss will be lesser. But
Sir,
how to limit the
okay.
junction temperature? So for that we need to, yes, limit the current flowing through the device.
Okay.
Are you getting the point? That is the only thing we are having.
Sir, but like here in this case, if the heat sink is actually cooler, then wouldn't more heat flow from the junction to the heat sink?
Yes, more heat will be flowing from junction to the sink.
So then there the junction temperature also would reduce, right? So
Then their junction temperature,
then like in that case, the junction temperature would also come down, right? If the heat sink is cooled.
no, we cannot say directly. Are you getting the point? Because heat sink temperature is 60 degree they have given, and they have
Okay.
not mentioned anything about the junction temperature.
Correct. Yeah.
So that's why we'll to consider junction temperature as it is,
Okay, sir. Okay.
right?
Okay. Sir, then one more.
Yes,
thing.
next.
Sir,
Yes, please. Yes, please.
sir, like in the gate characteristic that we found that we took VG into IG as P max. I didn't get how it becomes P max.
In gate characteristic,
We took VG into IG as P max, no, right?
that VG into capital IG.
Okay.
That capital IG means, the meaning is actually, you can check na, voltage VG, we are having voltage across gate cathode, and
Okay.
current flowing through the gate circuit is a capital IG. That is the magnitude, na?
Yes, sir. Yes.
So if you take the product of that maximum current, that is the IG, magnitude of the current IG into VG, that will be your maximum power loss only.
Oh,
Whether your
okay.
power loss will be greater than that of that VG into capital IG product, no, it will not. Because the thing is, we are using the pulse, na, gate pulse.
Gate pulse, yeah.
So for the simple thing is, we have given their relation. We have given the relation between average power and the maximum power.
Okay.
Right?
Yes, sir. Yes, sir. Okay. Got it. Okay, sir. Thank you.
Yeah. Next. Yes, please, Mahesh, Sainath. Sainath, do you want to speak something?
No, sir.
Okay.
Hello, sir.
Yes, please.
Sir, I had a doubt in overcurrent protection for this gate cathode circuit. We're using resistors now, sir, to limit the current.
Yes.
But sir, actually, when we use resistors also in a circuit, the current flowing would be the same, na, sir. If it is in series, then
No, na. How? You can check, na. You can check. Suppose I am having we are having with a 10 volt voltage source, right?
Yes, sir.
Across 10 volt, if I connected 2 ohm resistor, how much current will flow? 5 ohm, 5 ampere.
5
And
amperes.
same voltage source 10 volt, and if I connect the 4 ohm resistor, means I have added 2 ohm resistor more, how much current flow? 2.5 ampere. So current will decrease na. If you increase, if you put the resistor, definitely your current will decrease in that path.
Sir.
Are you getting the point?
Yes, sir.
Right? Because
And
ES we are keeping the same. ES we are keeping the same. And if I add the RES na, right? Or RES, or you can say RG, definitely that current will decrease na.
sir.
Right? Yes.
Sir, and why are we preventing or protecting from noise signal? That could you explain once again, sir?
Okay. The thing is actually, yes. This is having a relation with your Faraday's law of electromagnetic induction.
Sir.
We are having a gate cathode circuitry, and due to the surrounding noise, even now also where we are sitting, we are having a number of noise signals. Okay. And those noise signals are having, generally the frequency of the noise signal is very high, right? So you can check if the frequency of the noise signal is high, due to that there is a possibility of induced EMF in the gate cathode circuit. And due to that induced EMF, what is the function of that EMF? To circulate the current, na? Or that induced EMF, it may be assisting to your ES as well. So it may increase your VG also, right? So for that, we need to limit that induced EMF. That's why we are protecting SCR or the gate cathodes. And gate cathode circuit, you can check the voltage rating is very less, na? Your noise signal will not affect your load circuitry or the anode cathode circuitry, because in the anode cathode circuitry we are having a high voltage high current rating, but whereas in the gate cathode circuit we are having a less voltage and less current rating, na? And our gate cathode circuitry is very sensitive, na? It is having a less voltage, less current rating, so that's why that circuit is very sensitive. So due to the noise signal, there is a possibility of induced EMF. And for that, we need to, yes, protect it against the noise signal. Now, due to the noise signal, what is happening? Whatever the EMF is induced, that induced EMF is having a frequency which is same as that of your noise signal frequency. Means here, you can check in the gate cathode circuit, we are having a VG, IG, ES. Those are the DC, na? So those DC are not having any frequency. Okay. The thing is, whatever the induced EMF is there, that induced EMF is having frequency. So due to that frequency or due to that characteristic, we are taking the help of the RC filter, right? If the frequency is high, noise signal is having a high frequency, so our capacitor will provide the short circuit path, right?
Yes.
Like this. Okay.
Okay, sir. Thank you, sir.
Yeah. Yes, next. Okay. Right. Thank you. Thanks to all of you.